Night gathers like velvet poured across a quiet harbor, and the great stage of reality softens into view. Space and time present themselves not as machinery grinding with effort, but as a patient arrangement that lets motion choose the simplest way forward. In that arrangement, the most restful truth is also the most elemental. In the absence of interference, a path becomes straight, a rhythm becomes even, and an orbit becomes the graceful compromise between falling and moving sideways. The fabric does not shove, it permits. Stars, comets, dust, and light slide along the curves already inscribed by mass and energy, and the journey becomes a letting go rather than a pushing through. A constant speed for light steadies the script. With a single limit that never tilts, signals behave predictably from one end of the cosmos to the other. This constancy organizes time and distance into a dependable duet. Clocks and rulers, when tuned to this tempo, keep faith with one another according to quiet rules. The patterns that fall out of this principle are smooth. An ideal clock that rides high above a planet will tick a little more quickly than an identical clock near the surface, but it will do so with a regularity that invites trust. A fast traveler will experience fewer heartbeats between two star marks than a resting twin, yet the difference is precise rather than capricious. Elasticity without surprise makes a calm theater in which events can be charted and sleep can arrive without worry. Freefall reveals another gentle principle. Weight is not an inherent burden but the feeling of being held away from the natural path. Release the hold and strain vanishes. An orbit is therefore the most relaxed state available to a satellite. It is a continual fall that never concludes. The craft returns repeatedly to the same altitude because forward motion keeps the ground curving away beneath it. The result is a kind of cosmic floating that requires only minor corrections. This effortless balance extends from artificial satellites to moons and planets, all of them moving through arcs that arise from the shape of the surrounding geometry. Rest resides in alignment with that shape. Distance mutes intensity with a kindness that never fails. When light spreads, it shares its energy across growing spheres. Double the separation, and the brightness falls to a quarter. The same easing applies to gravity and to many other fields that radiate outward. Even the aftermath of violent encounters cannot stay fierce forever. Radiation thins, waves flatten, heat dilutes into the wide cold. Far from their sources, signals arrive as soft measures that instruments must coax from the background. The long reach of this dimming creates a universe where, paradoxically, immensity fosters quiet. The background glow that fills all of space is the remain of an early blaze that has been stretched into a gentle chill. Expansion draws wavelengths toward red, giving photons less energy and less urgency. What began as fiery brilliance now lives as a uniform bath only a few degrees above absolute zero, a calm sea that laps against every atom. Uniformity on this scale is one of the most relaxing facts that observation has offered. The same faint temperature is found in every direction to a remarkable precision. It suggests a youth smoothed by processes that favored evenness, and it leaves the present with a hush. Curvature provides guidance with more mercy than force. A massive body bends the stage slightly, and nearby paths slide into curves without any need for pushing. The trajectories are solutions to an optimization that nature performs continuously. The principle of least action is a doctrine of minimum fuss. Systems evolve along routes that cost the least when energy and time are balanced together. A thrown stone, a circling planet, a vibrating string of light all obey that quiet arithmetic. Symmetry becomes the lullaby beneath it. When a system looks the same from place to place, momentum stays conserved. When it looks the same across time, energy persists. These conservation laws are the promises that keep the play serene. Silence is the default between stars. Sound needs matter to carry it, and interstellar space offers only sparse atoms with enormous deserts between them. The loudest possible thunderheads, those born in supernova hearts or near colliding remnants, cannot make a peep across the void. Instead, their messages ride as faint changes in fields or as tremors of space itself. Even those tremors, the ripples that carry news of cataclysm, arrive as strains so tiny that only the most refined instruments have noticed them. Cathedrals are built to absorb noise and leave a clear echo. The cosmos behaves like that at scale. Gentle gradients rule much of the landscape. Time runs a touch more slowly near a massive body and a touch more quickly higher up. This vertical change is steady enough that engineers can compensate for it with precision. Navigation that guides ships and aircraft depends on those corrections. The presence of predictable gradients is not a complication, but a comfort. They exist like slopes in a garden, inviting a slow walk rather than a scramble. A clock climbing a mountain will shed infinitesimal fractions of delay, and on the summit it will keep a tempo that subtly favors the future. These shifts are poetic, but they are also practical, and their reliability deepens the pervasive sense of calm. Islands of balance arise, where multiple pulls combine in just the right proportions. In a two-body system, there exist points where gravity and motion match to create places of restfulness for small companions. Observatories take advantage of these sanctuaries because gentle station keeping preserves fuel and attention. A spacecraft that waits there enjoys a view tailored for watching the universe with minimal fuss. The idea generalizes through celestial mechanics. Careful placement yields quiet behavior. Harmony is not an accident. It can be found by listening to the equations and choosing a seat where the music is already soft. Cooling follows expansion like sleep follows twilight. As space stretches, wavelengths lengthen, energies drop, and temperatures decline. Gases that were once hot settle toward equilibrium with their surroundings. The long fate of most matter is not frenzy but composure. Clouds condense under gravity and ignite into stars, and later those stars fade, leaving embers that radiate away their heat across ages. The default trajectory bends toward quiet. Expectations founded on everyday friction can mislead. In daily life, motion slows because surfaces rub and air resists. In the wide arena beyond atmospheres and floors, such frictions vanish. Momentum retains its authority. A pebble pushed from a gloved palm would drift for centuries if nothing disturbed it. The absence of resistance becomes a revelation about what motion actually prefers. Stillness in this context is merely a special case. The broader tendency is to keep going, to preserve direction, to maintain rhythm. Understanding this removes a hidden anxiety from the mind. Not every change requires effort. Much of what happens is a continuation, and continuations are peaceful. Even the notion of direction gains a soft nuance. Simultaneity depends on motion and location. What is happening now at a distant star cannot be pinned down without choosing a frame of reference. Instead of adding confusion, this flexibility dissolves false rigidities. There is no single cosmic clock that orders all events. There are many legitimate clocks linked by elegant transformations. The result is a gentler picture of time, one that forgives differences between observers and replaces conflict with translation. The night sky embodies these principles in a simple image. Patterns of stars return in seasonal arcs because the planet turns and circles with dependable grace. Shadows of planets draw predictable lines on observatory detectors because gravity curves light the same way today that it did yesterday. When a comet appears, its path can be charted years in advance. When an eclipse is due, the hour can be written down long before the moon's shadow crosses a continent. Predictability at this level is not rigidity. It is a stable melody that allows themes to unfold without jarring surprises. The ultimate comfort lies in the idea that the largest structures and the smallest quanta both answer to rules that make chaos the exception. At immense scales, geometry and expansion smooth roughness into wide, even tapestries. At minute scales, fluctuations average into classical behavior whenever interaction with the environment becomes strong and the macroscopic world steadies into familiar shapes and movements. Between these tiers of description, life takes place. Breath rises and falls in a tiny raft carried by grand motions that ask nothing in return. The scene, then, is a hammock rather than a treadmill. The fabric holds and adjusts to weight without complaint. The occupant does not need to push to stay aloft. It is enough to rest within the weave that already supports all bodies and all beams of light. Tranquility is not borrowed. It is offered by the architecture of space and time themselves, which invite every traveller to move with the least possible strain. A young clerk walked each day along the cobblestones of Bern, carrying a satchel and a set of questions that would not release their grip. His desk at the patent office faced the quiet regularity of human devices: clocks, motors, telegraph improvements, all of them proposals for taming time and motion. He received them, inspected them, stamped them, and then returned to the puzzle that drifted like a soft cloud above the city roofs. If a beam of light were pursued at full speed, what would the chaser see? Would the wave freeze into a standing pattern? Experiments already suggested otherwise. Measurements from careful laboratories insisted that light kept the same pace from every vantage, whether the observer moved or not. This stubborn constancy became the first stone in a new path. He decided to trust the measurements completely. From that trust, a new harmony emerged. If light refuses to change its speed for any traveler, then space and time must bend their own measures to accommodate the rule. Distances contract for swift motion, durations lengthen. Simultaneity dissolves into a local agreement rather than a universal decree. These were not violent changes. They were gentle recalibrations that allowed the universe to keep one simple promise without tearing. In the quiet of 1905, he wrote the words that announced this insight, and the world learned that motion does not stack like everyday arithmetic. Instead, it composes with a graceful transformation that leaves the speed of light untouched and lets the laws of physics read the same in any constant drift. Another thought formed while he pondered falling and weight. If someone floats inside a sealed cabin far from worlds and stars, there is no way to tell, by local tests, whether the cabin sits still in deep space or accelerates upward with a steady push. Likewise, a person in free fall near a planet has no sense of weight while the descent continues. This parallel suggested a daring equivalence. Gravitational pull and acceleration share a deep identity. Build a theory around that identity and gravity will not be a force reaching across space. Gravity will be the shape of space and time themselves. Objects will follow curves set by that shape, and the sensation of weight will be the body's resistance to being kept on a path that is not its natural glide. He searched for the mathematics that could express this idea without compromise. Tensors and differential geometry became his grammar. In those symbols, the stage gained the power to curve, and curvature told matter how to move. Matter in turn told curvature how to form. This balance, written elegantly in field equations, replaced the picture of invisible tethers with a picture of paths that are simply straight within a bent arena. A planet does not feel a pull. It traces the easiest line through a landscape molded by a star. A ray of light does not stumble. It sails along a null path that hugs the bent contours around a Sunday. Proofs worthy of such a reimagining had to be patient and clear. The advance of Mercury's perihelion had long puzzled astronomers. Each orbit drifted a little more than Newton's rules predicted. When the new equations were applied to that problem, the number matched the anomaly as if a lock had found its key. Suddenly, the orbit's slow rotation was not a curiosity on a ledger. It was a natural consequence of the way mass sculpts the stage. Confidence rose, but telescopes demanded their own confirmation. If starlight grazed the limb of the sun, the path should bend by a calculable angle. A rare total eclipse offered a chance to measure the deflection without glare. Observers prepared glass plates and delicate instruments to capture the positions of stars when the sun's disk was masked. The results pointed toward the anticipated shift. The triumph did not arrive like a thunderclap. It arrived like a careful chorus, confirming a new key. Clarity did not mean coldness. The insights carried a kind of warmth, the warmth of simplification. A single constant for light replaced a stew of ether theories. A single principle for falling unified weight and acceleration. A single set of equations wrapped geometry and matter into a mutually responsive duet. Everyday experience still held its place, but it now sat inside a broader description that forgave the limits of intuition. Trains and clocks and beams showed how time and length adjust without drama when the world moves quickly. Planets and photons showed how curvature guides without grasping. He returned to the patent office while these ideas matured, then later to universities where chalkboards could host the new symmetries. Students watched as the calculus of curves transformed gravity from a whispering ghost into a readable script. The equations yielded solutions with personalities. A massive spherical body carved a gentle well that matched planetary orbits. A dense collapse led to horizons where escape surrendered. A universe that expands or contracts became a possibility not from speculation, but from the very structure of the field equations. Observers began to see the sky as a set of questions that had waited politely for the right language. The spirit of the work valued operational clarity. What could an observer actually measure inside a lab or on a ship? Thought experiments were conducted with care, little theaters where ideal clocks and rulers and light pulses performed. A man in an accelerating elevator feels weight. A beam crossing that elevator curves because the floor rises to meet it. Replace the elevator with a room in a gravitational field, and the outcomes match. The equivalence felt irresistible, and out of it rose predictions that could be tested. Time would pass more slowly lower in a gravitational well. Light would lose or gain frequency when climbing or descending. These were not philosophical curiosities. They were measurable drifts that could be coaxed from apparatus on Earth. What might have remained a collection of clever puzzles became, in practice, a navigational revolution. Precise timing between orbiting clocks and ground receivers required accounting for both speed and altitude effects. Engineers did not lament the adjustments. They used them. The sky became a lattice of coordinated signals because the theory provided exact corrections. A driver requesting a route or a ship seeking a harbor relied on equations born at a desk where inventions had once passed for judgment. The transformation from clerk to theorist to quiet guide of satellites traced a line as elegant as any geodesic. Yet the atmosphere of the work kept a certain gentleness. The scholar who imagined riding a light beam did not claim that the universe needed drama to be profound. He suggested instead that the highest order of beauty reveals itself when assumptions are released and principles are allowed to determine the shape of things. Relativity did not agitate the cosmos. It offered the cosmos permission to be consistent. Motion depends on the frame used to describe it, but the laws remain unchanged across all frames that drift without acceleration. Gravity depends on the distribution of energy and momentum, but free fall remains the same for all bodies regardless of their composition. Equality in these senses is a quiet equality, a promise that nature keeps without fanfare. The confirmation from eclipses, orbiting planets, and later from radio signals skimming the sun's edge did more than check boxes. They taught a method: trust high-quality measurements, write down the simplest principles that respect them, allow mathematics to generalize those principles without adding frills, then ask the world to answer. Each answer arrives in its own tempo, sometimes as a gradual accumulation of data, sometimes as a single decisive graph. In this way, the sky becomes a teacher with a soft voice but impeccable memory. Stories often seek an emblem, and here a simple image will suffice. Imagine two stones dropped from a tower, one heavy and one light. They fall together, not because some secret hand equalizes them, but because their paths ignore what they are made of and attend only to the shape of the stage beneath. That shared attention is the essence of the insight. Equality of freefall replaces hierarchy of substance. The flaw that interrupts them is the only source of the sensation called weight. Remove the flaw, and the stones find a restfulness that appears paradoxical until geometry explains it. From the quiet corridors of a Swiss office, to the chalk dust of lecture halls, to the delicate ink of field notebooks taken to distant islands for eclipses, a patient revolution unfolded. It resolved confusion not by adding complexity, but by loosening the grip of assumptions that had gone unquestioned. Space and time did not become capricious, they became honest. Clocks ticked according to their paths, rulers shrank according to their speeds. Mass molded the arena with curves gentle enough to guide planets, and strong enough, under extreme compaction, to create horizons from which even light cannot flee. Each element found its place in a tapestry that values consistency over spectacle. The facts are restful because they reward trust. The approach taken by the young clerk turned physicist invited a partnership with reality rather than a struggle. Observers do not impose order on the sky. They listen for it, infer it, measure it, and then write it down in the fewest words. That attitude, more than any single equation, gives the story its calm. Where others sought the ether, he accepted the absence of it. Where others insisted on absolute time, He allowed simultaneity to become relational. Where others treated gravity as a force, he let geometry assume the role. With those permissions granted, the universe answered in harmonious detail. The surprise begins with how softly the world refuses old habits. For centuries, motion had been taught as a negotiation between push and pull, as if every change required a hand on the shoulder. Then a careful look showed that the stage itself carries the instructions. Gravity does not grab, it shapes. Objects do not strain, they comply. This replacement of force with geometry is the quietest upheaval in science. The shock lies in discovering that calm rules sweep away the need for invisible chords. Curved lines in a flexible arena replace the picture of hooks and ropes. The mind expects drama at the root of things and finds instead a patient diagram. Even the shape of a triangle becomes a clue. On a flat table, 3 angles add to a neat 180 degrees. Near a massive body, light beams used as ruler and straightedge trace a triangle whose angles sum to a little more. No one pushes these beams off course. Space itself adjusts so that straight is no longer the same as straight in a Euclidean sketchbook. The surprise is not that paths bend. The surprise is that bending is normal while flatness is special. A planet's orbit is not a balance between a forward dash and a tug from the side. It is the natural curve of a road that happens to be gently banked around a star. Time joins the quiet rebellion. Daily life trains the mind to imagine a single clock in the sky. The actual structure is more forgiving and more subtle. What counts as simultaneous depends on motion and location. 2 events that match moment for one traveler may unfold in sequence for another. There is no argument between them because the laws connecting their descriptions remain exact. This is not chaos. It is a flexible fabric with a fixed thread count. The constancy of light speed provides the standard stitch, and the transformation that relates one description to another preserves the pattern. Calm prevails while common intuition loosens its grip. Energy and mass share an identity that also feels like a whisper rather than a shout. The famous equivalent sits in the equations as a line of clean algebra, a statement that energy carries inertia and that mass stores energy. The consequences range from the fire in the heart of stars to the delicate pressure of light on a foil sail. The shock is not in the number itself. It is in how ordinary objects reveal latent power when their bookkeeping is written correctly. The world does not add machinery to explain this. It simplifies the ledger and lets equivalence handle the rest. Weight loses its sacred status. Experiments with pendulums, torsion balances, and freefall confirm that composition does not matter for descent. Lead and wood, copper and glass all follow the same curve when released. The grand idea behind this universality is austere. The geometry that defines straightest time like paths pays no attention to the labels on the falling bodies. If a scientist packs a suitcase with different substances and drops the lot in a vacuum, the case remains neat. Everything floats together because the stage ignores their differences. The old expectation that denser things should fall faster dissolves under measurement, as surely as mist under Sunday. Causality acquires edges that are firm yet gentle. Nothing outruns light, so influence respects a clean cone in the map of events. Inside that cone, signals can travel. Outside it, no message can intrude. The boundary carries no fence or gate. It is written into the way time and space trade rolls when speeds approach the high limit. The surprise here is structural. A principle about what counts as possible emerges from the geometry rather than from an external referee. Even the concept of before and after becomes local. Different observers slice the loaf of space-time at different angles, and still the loaf remains whole. The laws ensure that all slices agree on what can affect what. Redshift and blue shift of light reveal another quiet departure from expectation. Climb upward out of a gravitational well, and a photon gives up a little frequency. Descend, and it picks some up. The shift is slight near familiar landscapes, yet precise and inescapable. Time's rate is implicated in the effect, and instruments register the change without complaint. The surprise for a newcomer is that nothing happens to the photon along the way in any mechanical sense. The stage's geometry accounts for the adjustment, the world changes its bookkeeping, and the measurement follows. Instruments sensitive to rotation add texture to the story. Spin a ring of light in opposite directions around a rotating mass, and the travel times differ by a minute amount. The stage drags a bit, as if a swirling ladle had stirred the broth of space and time. The effect is gentle and becomes obvious only near compact objects, or when high-precision gyroscopes patiently integrate tiny deviations. The shock is that what had seemed empty and featureless acquires a property akin to viscosity. Not a literal syrup, but a measurable tendency of the frame to be carried with spinning matter. The smoothness remains, yet the smoothness has character. Horizons introduce calm boundaries with startling consequences. Approach a compact region where escape speed climbs to light's value, and the math says outward paths fold into the geometry before they can carry messages away. From far off, a falling clock appears to slow, its signals stretched into red, and then into silence. From the falling clock's own vantage, nothing special occurs at the crossing. The stage handles both stories without contradiction. The shock lies in accepting that two pictures, each internally consistent, differ so completely in what can be seen. Again, the laws reconcile them, and again the manner is gentle rather than violent. A horizon is not a wall, it is a limit written in the chalk of geometry. Cosmic expansion carries a similar tone. Galaxies do not bomb away from one another through a pre-existing emptiness. Instead, the metric that defines distance grows. Light between clusters stretches, and the songs of ancient atoms slide to lower notes. There is no center from which everything flees. There is a scale factor that increases, and with it the map's grid lines slowly widen. The shock here is conceptual. Motion without motion. Separation without running. A universe can grow not by things speeding through space, but by space itself, relaxing its woven pattern. Tides add a final hint of how gentle rules can produce strong experiences. Two ends of a body fall along slightly different curves and feel a stretch or squeeze as a result. The cause is not a direct pull, but a difference in geometry across the body's length. Stand near a planet, and the water rises under the moon, then under the Sunday. The mind expects a single finger of force, and receives instead a story of neighboring paths diverging or converging. Weak near familiar terrain, these tidal effects become decisive near compact masses. The shock is cumulative. Simple, calm rules, applied to situations with high curvature, produce the drama that observers later call extreme. What emerges from these examples is an inversion of expectations. The deepest laws aim at economy. From them flow deviations that seem extravagant only because perception was trained by friction and straight rulers. Geometry governs motion. Synchrony depends on frame. Energy and mass mirror each other. Influence respects cones in a diagram more faithfully than it respects intuition. Horizons speak in limits rather than in barriers. Expansion increases separation without issuing any order to run. Tides express difference rather than strength. The amazement is real, and yet it arises not from exotic additions, but from subtraction. Assumptions are removed, and the world becomes both stranger and more serene. Prediction becomes the final assurance. Where intuition aches, equations proceed with quiet authority. Precession angles, time dilations, path deflections, and frequency shifts appear on paper and then on instruments. The calm that shocked on first encounter turns into a dependable companion. The stage does not tire. It does not capriciously change its frame. It offers curves to follow and rates to keep. In that reliability lies the comfort that closes the circle. The world surprises by being simpler than habit allowed, and it keeps surprising by remaining that way in the face of scrutiny. Starlight arrives as a patient courier, carrying news in the language of frequency and angle. A glass plate cooled by night air can hold this news as tiny dots, each one a message from a place so far that time itself seems to hum between. During a rare darkness at noon, when the moon hides the sun, distant points slide just enough to betray a gentle bend in their path. The plates reveal a displacement that matches a calculation made with quiet confidence. The sun does not tug the beams. The beams follow the curvature that mass has written into the sky. A handful of arcseconds, faithfully recorded, become a soft signature of geometry. Another signal rides not in position but in color. Climb out of a gravitational well and a photon yields a touch of energy. Descend and it gains a touch. A tower on a university campus can host the proof. A beam sent upward loses a fraction of its frequency, a shift so small that meticulous resonance tricks are needed to notice. The result is not theatrical, yet the consequence is profound. Time rates differ with height, and light keeps the account with perfect bookkeeping. Rockets later confirm the effect with higher climbs, but even the original vertical span whispers the same truth. These measurements transform abstraction into instrument readouts, and the cosmos becomes a laboratory with steps and landings. Distance itself can be measured by timing whispers. Send a radio pulse toward Venus when the planet moves behind the Sunday. The echo returns a touch late, not because the transmitter failed, but because the pulse creeps through curved geometry and takes a slightly longer route in time. The delay, predicted by equations that treat mass as a sculptor of intervals, agrees with the shape of the sun's influence. Engineers who once learned to count in microseconds learn to accept extra microseconds as a gift from the stage. Time becomes a ruler for mapping invisible hills and valleys carved into spacetime by nearby bodies. Sometimes a single galaxy acts as a lens, turning light from a more distant one into arcs and rings. Telescopes resolve these shapes with crystalline detail, and the sight resembles frost traced on a window. Alignment creates circles that bear a name for the person who predicted them. Imperfect alignment creates swirls and crescents. Each curve is a map of mass, luminous and hidden. By tracing it, astronomers reconstruct the distribution of matter in the lensing system, even the matter that emits no light. The method transforms gravity's quiet shaping power into a tool for cartography, and the result is a portrait of structure painted without touch. Microlensing adds a smaller scale to the canvas. A star passes in front of another from the viewpoint of Earth, and the brightness of the background star swells and subsides in a symmetrical pattern. If a planet orbits the foreground star, a secondary ripple appears. No photon reveals the planet directly, yet the timing and shape of the light curve announce its presence. The technique finds worlds that other methods would miss, especially cold ones far from their suns. The calm bending of trajectories provides a means to weigh and to count, and the tally grows with patience. Spectroscopy divides starlight into bands that resemble the strings of a harp. Each element writes a set of dark lines into the spectrum, and those lines shift when the source moves or sits in curved time. A star nearing its end draws matter from a companion, and the lines dance back and forth with the rhythm of the orbit. A distant galaxy's lines slide toward longer wavelengths, not because it speeds through space, but because space expands as the light travels. The shift is not a blur of chaos. It is a precise record of the scale factor's growth. By collecting spectra across many distances, observers compose a history of expansion written entirely in tones. Variable stars supply another kind of clock. Some brighten and dim, with periods that reveal their intrinsic luminosity. Compare that luminosity with the measured brightness and distance follows. These standard candles extend the measuring stick beyond the reach of parallax, giving a ladder that climbs from nearby neighborhoods to remote clusters. With this ladder in hand, entire galaxies become yardsticks. The timing of a pulsation, read through glass and electronics, turns into a number of light years. The universe grants a tape measure that is soft in tone and immense in length. Atomic clocks refine the portrait of time's elasticity. Two clocks, one on a mountaintop and one at sea level, tick at slightly different rates, just as the equations advise. Fly clocks eastward and westward in aircraft, then compare them with a clock that stayed home, and the differences align with the combined effects of speed and altitude. Orbiting clocks aboard navigation, satellites tick faster because they sit higher in the gravitational field, then slower because they move quickly, and the net effect is corrected in the algorithms that guide navigation. The practical world accepts these corrections not as curiosities but as necessities. Devices tell positions because time has been weighed and adjusted with respect for geometry. Pulsars offer a more distant timing grid. These rotating remnants broadcast radio pulses with extraordinary regularity. When one orbits a companion, the arrival times of pulses shift in a way that reveals the orbit's shape and orientation. Some pairs show a steady decrease in orbital period as energy drains away through effects predicted by the field equations. Without lasers or rockets, without direct interference, observers watch a clock system change in sync with calculations. A tick lost here, a nanosecond there, and an invisible energy budget balances. The staccato beat of a dead star becomes a metronome for testing gravity's calm rules under high density. Light itself can paint the early universe when sensitivity reaches subtlety. A faint glow fills every direction, nearly uniform, with fluctuations so small that only space telescopes can measure them cleanly. The pattern of these small temperature variations carries the imprint of acoustic waves in a hot plasma long ago. Peaks and troughs in the power spectrum speak about curvature, composition, and the interplay between pressure and gravity. The measurement turns the night into a fossilized symphony, and analysis reads its chords. From this data, a consistent picture emerges of a cosmos that is close to spatially flat on large scales, with matter and radiation, and a quiet form of energy sharing the budget. Gravitational lensing on the largest scales adds texture to that picture. Weak lensing, a statistical distortion of galaxy shapes across wide fields, maps the clumpy distribution of matter over cosmic time. The effect is tiny for any single galaxy, but a survey of millions reveals coherent shears that betray the scaffolding of the cosmic web. The method requires careful calibration, yet the reward is a three-dimensional view of structure formation. The universe yields its skeleton through the smallest of nudges, like footsteps detected through vibrations in a wooden floor. Precision astrometry provides motion pictures of the sky that stretch across years. Instruments measure positions with micro-arcsecond accuracy, enough to catch planets tugging their stars side to side, and enough to detect the slow drift of clusters as the solar system moves. Relativistic light bending near the sun and planets must be accounted for to reach this accuracy, which turns the theory into a tool that sharpens the image. The dance of positions becomes a ballet directed by geometry. Without that choreography, the performance would blur. Eclipses, redshifts, time delays, rings of light, clocks in flight, pulsars ticking in the dark, whispers from the first plasma, the faint shear of millions of galaxies, all are chapters in the same listening practice. Instruments lean closer to the universe and hear what it repeats with patience. The messages do not contradict each other. They reinforce a framework where mass curves the stage, where time keeps multiple tempos synchronized by simple laws, and where light faithfully reports every contour it crosses. The more carefully the listening proceeds, the more detailed the map becomes, and the map remains consistent even as it grows. This listening carries a mood suited to rest. There is no need to force answers from the sky. The sky offers them when asked with respect for precision and for the limits of noise. A star's deflection near the sun, a clock's shift on a mountain, a ring of blue light wrapped around a red core, these are not acts of spectacle. They are acts of calm coherence. The cosmos keeps rhythm and writes it into beams that travel for eons without forgetting. On a clear night, that knowledge lends peace. The quiet courier continues its journey, and anyone with a patient instrument can read the envelope and understand. A photograph of the whole sky in microwave light looks almost like a single color wash. The temperature sits near 2.725 Kelvin, as if the universe tucked itself beneath a perfectly even blanket that glows with a faint ember heat. Only when sensitivity climbs to exquisite levels do tiny freckles appear. Their amplitudes are measured in tens of microkelvin, a few parts in 100,000. This extraordinary smoothness brings comfort to the eye and a riddle to the mind. How did such a vast expanse settle on almost the same temperature in every direction when many of those directions are so far apart that no signal could have traveled between them in the early epochs to even things out? That riddle wears a name shaped by geometry. Draw a sphere centered on any observer at the time the afterglow was emitted. Its radius is set by how far light could have moved since the first luminous atoms formed. Points on opposite sides of that sphere lie outside one another's reach within that early interval. They had no chance to swap heat or trade instructions, yet their temperatures match to astonishing precision. This is called the horizon problem. It is like finding two distant campfires that never exchanged a spark, burning with identical flames and identical crackling rhythms. Either the camps once shared a closer intimacy than distance suggests, or the universe contains a mechanism that forced uniformity without communication. Another layer of calm, equally puzzling, appears in the shape of space itself. Measurements of the microwave afterglow, of large-scale structure, and of the way light paths join and part all indicate that on grand scales the geometry is very close to flat. Triangles add their angles almost as they would on a chalkboard. The curvature, if any, is small and globally balanced. This near flatness is precarious in ordinary dynamics. A slight departure in the early era would amplify over time, sending the universe toward rapid collapse or runaway curvature. The fact that it did not suggests an early condition, tuned with care, or a process that drove the curvature toward neutrality. The puzzle is not a shout, it is a quiet balance that seems to have been upheld with remarkable fidelity. The smoothness is not total. Those tiny freckles carry deep meaning. They trace sound waves in a young plasma where photons and ions moved together. Pressure pushed outward while gravity gathered inward, setting up oscillations that left an imprint on the sky. The sizes of the peaks in that pattern and the spacing between them reveal proportions of matter, radiation, and a subtle energy that influences expansion. Yet the mere smallness of the fluctuations raises a question about initial conditions. If gravity tends to amplify clumps, why did the early canvas begin so evenly spread that only slight ripples were available to grow into galaxies? Gravity prefers to sculpt. Smoothness resists that impulse. The beginning seems to have chosen restraint. There is a second sense in which smoothness harbors surprise. Thermal entropy in a hot plasma is high, but gravitational entropy is another ledger. Uniform mass distribution corresponds to low gravitational entropy because there are many more ways for matter to clump than to remain evenly spread. The ultimate high-entropy gravitational state is a scattered population of black holes, or even a single enormous one. By that measure, the early universe occupied an incredibly special state. It was hot and bright, but gravitationally pristine. That choice of state sets the arrow of time, because as clumps form and structures grow, gravitational entropy increases and processes unfold that lead stars to burn and lives to be lived. The arrow feels gentle in experience, yet it was fixed by an uncommon calmness at the start. Peculiar motions also speak to the serenity. Galaxies ride the general expansion like boats on a rising tide, but each boat can have its own small drift. Surveys show that these drifts are present, yet modest compared with the overall outward flow on very large scales. Over hundreds of millions of light-years, velocities average toward the Hubble rhythm. This coherence builds a sense of cosmic repose. A universe with wild bulk flows would smear structures and complicate the reading of the afterglow. Instead, the large-scale map displays a nearly uniform stretch with superclusters and voids layered gently upon it. At intermediate scales, the web of matter threads into filaments and nodes where galaxies gather. Even here, the pattern keeps an air of restraint. The distribution follows statistical rules that arise from those primordial ripples evolved through gravity and cosmic expansion. Computer simulations fed with initial fluctuations of the measured amplitudes and spectra reproduce forests of filaments that resemble observations. The match is not only visual, it is quantitative. Correlation functions and power spectra, measured in galaxy surveys, align with predictions from simple initial conditions guided by general relativity and pressureless growth after the plasma era. This suggests that the recipe for calmness in the background and the recipe for complexity in the foreground are compatible, yet it does not banish the question of why the first ingredients were so finely balanced. Photon diffusion in the early plasma adds one more polish to the smoothness. Before atoms formed, photons scattered again and again off free electrons, wandering like fireflies in fog. This wandering smeared out small-scale temperature contrasts. The effect, called diffusion damping, acts like a soft focus filter on the primordial photograph. It reduces structures below a certain angular scale, ensuring that the afterglow remains a gently variegated field rather than a speckled mess. The mechanism is simple physics of scattering and heat exchange, yet its presence makes the large-scale calm even more striking. The sky's smoothness is not accidental noise, but the outcome of well-understood processes layered atop an already even initial field. The sound horizon deserves special attention. There exists a characteristic scale set by how far sound could travel in the young plasma before the afterglow decoupled from matter. This distance imprints itself as a preferred separation between galaxies in the later universe. Surveys detect a slight enhancement in the probability that two galaxies sit that far apart. This feature, the Baryon Acoustic Oscillation Scale, acts as a standard ruler that confirms the uniformity in a new way. The ruler appears the same in all directions on the sky within experimental limits, reinforcing the impression that the vast expansion is isotropic. If the universe had substantial shear or twist on enormous scales, this ruler would warp. Its steadiness testifies to a placid kinematic landscape. The quiet background has room for hints that invite caution. Certain low multipole modes in the microwave map have shown alignments that tempt speculation about large-scale anomalies. Masks for foreground dust, instrument systematics, and statistical happenstance complicate any dramatic inference. Most analyses favor the interpretation that the sky remains consistent with random fluctuations drawn from the measured spectrum on top of an almost uniform mean. This careful humility is itself calming. The data do not rush to theatrical conclusions. They lean toward a picture in which near uniformity reigns while tiny, stochastic ripples seed all later structure. Homogeneity also emerges in counts of galaxies. On scales below a few 100 million light-years, clumpiness rules. Above those scales, the average density settles toward a constant. The transition resembles the way ocean waves look choppy near a boat but merge into a flat horizon from a higher altitude. This transition supports the idea that a single set of initial rules applied everywhere, that no vast region plays by different laws. The calmness is democratic. It treats all directions equally, and all large neighborhoods with the same steady behavior. The puzzle remains an invitation rather than a frustration. Smoothness on grand scales provides the canvas on which every later drama unfolds. Yet the circumstances that produced such an even canvas call for explanation. If the universe began with arbitrary conditions, one would expect more variation in temperature across opposite corners of the sky, sharper curvature in global geometry, and wider deviations from the Hubble flow. Instead, there is a long, quiet exhale written into the first light. The task is to understand what set that exhale, whether by an episode of special dynamics or by a principle that selects simple beginnings. The reward for stating the puzzle plainly is a deepened sense of ease. The cosmos does not appear tuned for spectacle. It appears tuned for coherence. The same numbers keep showing up in independent measures of the afterglow, in galaxy clustering, in the relative heights of acoustic peaks, in the distance scale inferred by different ladders. Harmony across methods calms doubt. Against that harmony, the open question of why the first state was so uniform becomes a soft challenge, the kind that invites long contemplation and careful thought. The sky says, "I am even, and I am vast." Understanding why it speaks so evenly is the next gentle step in listening. Waves travel through oceans by lifting and lowering water. A different sea spans the cosmos where the medium is geometry itself. When massive bodies change shape in an asymmetric dance, they send ripples outward at the speed of light. These ripples stretch one direction while squeezing the perpendicular, then trade rolls a heartbeat later. The effect is a strain rather than a shove, a rhythm of lengthening and shortening that passes through anything without resistance. The numbers that describe it are tiny. A strong event far away changes the separation of two test points by a part in 1,000 billion billion. It is like altering the distance from Earth to the nearest star by less than the width of a human hair. Such delicacy seems more like a silence than a wave, yet it carries energy and information with unfailing fidelity. The rule that sources must be quadrupular gives the waves their unhurried character. A spherical explosion radiates light, but cannot radiate this kind of gravitational disturbance, because equal expansion in all directions leaves the curvature unchanged at a distance. The chorus begins only when the mass distribution deforms in a lopsided way. Two compact objects orbiting each other in a tightening spiral make the perfect instrument. As orbits shrink, the frequency rises, the amplitude grows, and the waveform traces a chirp that climbs in pitch and loudness until the bodies merge. The signature is not chaotic. It is a pattern that follows equations precise enough to let computers draw the expected curve before any signal arrives. To catch such a faint strain, instruments must quiet themselves to a degree that stretches the meaning of stillness. An interferometer accomplishes this with right-angled arms several kilometers long. A laser splits into two beams that travel down the arms, strike mirrors, and return to recombine. When the arm lengths change relative to one another, the interference pattern shifts by a fraction of a wavelength. Every source of noise must be suppressed. Mirrors hang on multi-stage pendulums to isolate them from ground tremors. Seismic hum is filtered by elaborate suspensions. Thermal fluctuations are tamed by carefully chosen materials and vacuum enclosures. The laser frequency is stabilized until it performs with monk-like patience. Only then can a passing ripple draw a trace distinguishable from the breathing of the earth. The first clear signal recorded by such instruments was brief yet unmistakable. A low thrum rose to a brighter note in a fraction of a second, then ended. Analysis matched the sound to two heavy black holes that had spiraled together over eons and fused. The distance was measured in hundreds of megaparsecs. The strain at Earth was on the order of 10 to the minus 21. From that delicate imprint, astrophysical facts unfolded. The masses of the participants, the final spin of the remnant, and the energy lost to waves were recovered with uncertainty bands that narrowed as templates improved. A new sense had opened, one that neither needed light nor cared about dust. Soon additional signals arrived, each with its own character. Some came from black holes of different masses. One bore the hallmark of neutron stars colliding, a longer and more intricate chirp that ended in a flash of high-energy light seen by orbiting telescopes. Behind that flash, optical observers found a fading blaze in a small galaxy, colored by the opacity of freshly forged heavy elements. Spectra showed features consistent with R-process nucleosynthesis, the family of reactions that build gold, platinum, and other precious nuclei when neutron-rich matter is stirred and ejected. The quiet wave carried the date and time of the collision. Photons painted the aftermath. Together they told a story about where some of the periodic table is made, a story that had waited since the first stars for an instrument calm enough to hear the opening note. The polarizations of these ripples add to the descriptive power. In general relativity, two independent modes, twist and stretch, space in patterns that detectors at different orientations can disentangle. A network of observatories spread across continents compares arrival times and relative strengths to triangulate positions on the sky. Although the initial error regions are broad, the method improves as more instruments join the network. The same timing triangulation turns the signals into standard sirens. If the waveform provides a direct estimate of distance, and if an electromagnetic counterpart gives a host galaxy, and thus a redshift, the pair together offer a way to chart cosmic expansion without relying on traditional distance ladders. The tones of spacetime itself become rulers for the largest scales. Another search listens for a background of overlapping waves from countless distant sources. Superpositions of many faint chirps can create a stochastic hum, a kind of gravitational static that pervades the universe. Terrestrial interferometers chase this hum at frequencies of tens to hundreds of hertz. On much longer timescales, a different approach becomes sensitive. Millisecond pulsars act as ticking beacons. If a slowly varying background of nanohertz waves washes through, the arrival times of pulses from many pulsars will wander in a correlated way. Arrays of telescopes that monitor dozens of such pulsars have reported evidence consistent with a background likely produced by supermassive black hole binaries in distant galaxies. The pitch is low, the rhythm spans years, and the inference rides on statistics. Even so, the picture that emerges is of a universe where gentle vibrations ring across all scales, from stellar remnants to giants at the hearts of galaxies. Burst searches add yet another mode of listening. Some events may radiate waves for only a brief instant with no clear chirp pattern, collapses of asymmetric stellar cores, cosmic string cusps if they exist, or sudden phase transitions in the early universe could fall into this category. Algorithms scan the data stream for unmodeled transients that rise above the noise. So far, compact binary coalescences dominate the confirmed catalogue, but the door remains open. The quiet ocean may yet send a singular splash that illuminates a process not seen in any other band. There is also the possibility of a memory effect. After a strong burst passes, space-time may settle at a slightly different configuration than before, leaving a permanent offset in distances. This is not a jolting jump, but a subtle step, like a tiny adjustment of a hammock after a person shifts position. Detecting such a step requires exquisitely stable baselines and long integrations. The effect would provide insight into how energy and momentum are carried away by the waves, and how the non-linear nature of gravity records the passage of intense disturbances. The future of this listening practice moves towards space. A constellation of spacecraft separated by millions of kilometers, linked by laser ranging, will form an interferometer sensitive to millihertz waves. This band contains signals from massive black hole mergers in early galaxies, tight binaries of white dwarfs within our own galaxy, and possibly whispers from cosmological processes at very high energies. Operating beyond Earth's restless ground and free from atmospheric disturbances, such a mission will observe a sky that sings in a lower register. Calibration demands will be severe. Formation flying must maintain arm-length stability to picometers over millions of kilometers. Laser photometers must read phase with extraordinary care. Yet the technological path is clear, and demonstration missions have already shown that quiet measurement is possible even in the harsh environment of orbit. Continuous waves from asymmetrically spinning neutron stars offer a complementary target. A slight mountain on the crust of such a star, only centimeters high, can radiate a steady tone as the star rotates hundreds of times per second. The amplitude is small, but long integrations can pull the signal from noise if the rotation frequency and its derivatives are tracked accurately. Discovering such a line would probe the rigidity of neutron star crusts and the interior physics that allows or suppresses deformations under enormous gravity. Here again the theme holds. Gentle waves expose intense conditions by arriving with minimal disturbance. The philosophy that guides all of this work is simple and patient. Build instruments that quiet themselves until the world speaks at the desired level. Model expected signals without ornament, then let data test the models. When surprises appear, trace them back to hardware, environment, or nature with equal humility. The reward is a map of violence drawn by the softest pen. Black holes merge without emitting light, yet their unions are now events with times, masses, distances, and spins recorded. Neutron stars collide and write both in gravity and in color across the spectrum. Supermassive black holes in distant galactic centers stir a background that tugs on the punctuality of pulsars in our own sky. The calm conveyed by these facts does not erase their grandeur, it refines it. Waves that thread the cosmos change every length by less than an atom's width over kilometers, and yet in aggregate, they reveal a history of interactions at energies beyond the reach of any laboratory. They do not need to roar. They arrive as disciplined fluctuations that instruments can welcome without strain. The universe breathes in slow measures, and with every detected ripple, the sense of that breathing becomes clearer. A listener could imagine laying a hand on the fabric and feeling it lift and fall with an immense, steady respiration that has been underway since the first stars formed and will continue long after current watchers have fallen silent. A cup of tea cools on a windowsill and never warms itself by borrowing chill from the room. Clouds diffuse and do not gather into sharp lines without a reason. Breath leaves a mark on cold glass and fades in quiet certainty. These small assurances express a deep principle. There exists a direction in which ordinary processes prefer to unfold. The story is named by a single quantity that tallies possibility. Entropy counts the number of microscopic arrangements that fit a macroscopic description, and the count tends to rise. The rule is not a command shouted by nature. It is a gentle leaning, a statistical preference that becomes overwhelming for large systems. The arrow of time follows that leaning, pointing from configurations with few compatible microstates toward configurations with many. The origin of this preference lies in the difference between detail and summary. At the microscopic level, the equations that move atoms and fields are reversible. A movie of a single collision between molecules can be played backward without violating those laws. At the macroscopic level, the eye does not track each particle. It observes temperature, pressure, density, and shape. Many micro descriptions correspond to the same macro description. A sugar cube dropped in water dissolves because there are enormously more ways for its molecules to be dispersed than to be arranged as a neat block. Dissolution is not urged by force, it is invited by combinatorics. This perspective carries a calm explanation for everyday irreversibility. Scrambled eggs do not unmix not because motion equations forbid it, but because the path to unmixed states is a needle's eye through a space vast with alternatives. A rare fluctuation could, in principle, reassemble order, but the timescales dwarf any patience. The second law emerges as probability, asserting itself with quiet authority. For systems with Avogadro scale numbers, the odds favor an increase in entropy by such margins that deviation is practically invisible. The comfort comes from the reliability of this trend, and from the understanding that it rests on counting rather than on mystery. A question rises like a small eddy in a slow river. If the microscopic rules are reversible, why does the macroscopic book keep an irreversible ledger? The answer invites a boundary condition. For the arrow to exist, the world must begin in a state of unusually low entropy for its gravitational degrees of freedom. Hot matter alone does not fix the problem. Gravity prefers clumpiness, and a uniform mass distribution is special because it offers few configurations. As structure forms, gravitational entropy increases. Stars ignite, galaxies assemble, and the inventory of possibilities blossoms. The direction marked by entropy growth becomes the direction remembered as future. The arrow is not built from local dynamics. It is drawn by an initial simplicity that leaves room for complexity to grow. The calculus of heat makes this story precise. Temperature defines how energy spreads. When two bodies touch, energy flows from the hotter to the cooler, because that exchange opens access to more microstates overall. Equilibrium arrives when no net flow increases the count further. The relaxation toward equilibrium is slow or fast depending on pathways, yet the destination is always the same. Detailed balance, asymmetry and transitions at equilibrium, codifies the stillness reached when all allowed exchanges cancel on average. Away from equilibrium, currents circulate like gentle winds, converting gradients into a harvest of entropy. Chemical reactions drift toward mixtures that maximize multiplicity given conservation laws. Diffusion smooths density differences because randomness explores space and finds myriad ways to blur sharp edges. Fluctuations persist even in calm. A small system can buck the trend for a short interval, exporting entropy into its environment or drawing order inward. This behavior is captured by the fluctuation theorems, results that quantify how the probability of a temporary entropy decrease is exponentially suppressed relative to an increase of the same magnitude. The theorems restore a sense of balance to the picture without undermining the overall arrow. For nanoscale machines and biomolecules, these gentle corrections matter, allowing life's molecular motors to operate efficiently while still paying the unavoidable cost of disorder creation in their surroundings. Information enters the stage as a sibling of thermodynamic bookkeeping. To erase a bit in memory is to compress possibilities, to fold many microstates into one. That act generates heat, and the minimum average energy cost per bit has a simple expression in terms of temperature and a constant that carries the units of action. The principle establishes an intimate tie between knowledge and heat, between computation and the arrow. As records are made and later cleared, entropy grows. The production of memory has a thermodynamic footprint. The mind's experience of time's direction aligns with the physical cost of storing traces of events. Black holes provide a grand canvas for the arrow written in geometry. A horizon's area, measured in appropriate units, behaves like an entropy. When matter falls in, the area grows. When two holes merge, the combined horizon is larger than the sum of the parents' areas. Radiation from quantum fields near the horizon gives the hole a temperature and implies that its entropy is proportional to area rather than volume, a hint that the fundamental bookkeeping of gravity may live on lower dimensional boundaries. A generalized second law counts ordinary entropy outside plus horizon entropy, and finds that the total does not decrease. The soft insistence of the arrow thus extends to the most compact structures known, guiding vast processes with the same quiet bias that cools tea. Where gases and radiation disperse, complexity can grow at the margins between sources and sinks. A star shines by fusing light elements into heavier ones, emitting energy that pours outward through planetary atmospheres and out again into space. The gradient between hot surface and cold sky supports cycles, weather patterns, and metabolisms that temporarily maintain local order. These pockets of organization are not violations. They are a means through which entropy increases elsewhere more than the local decrease. The arrow gives room for patterns to form as long as they ride on currents that, in total, favor dispersion. A subtlety lies in coexistence of multiple arrows associated with different subsystems. A chemical reaction network might display a slow relaxation toward a fixed point, while a driven electronic circuit registers a periodic steady state sustained by an alternating source. Both contribute to entropy production in their environments, yet their internal measures of progress differ. The many ways of leaning forward do not conflict. They harmonize under the same global accounting. The quietness of the cosmos at large does not preclude spirited motion in small niches, it frames them. Time itself suggests an even more delicate picture in contexts where a preferred global time parameter is absent. In covariant descriptions of fundamental physics, one may define a flow of time emergent from the state of the system, with temperature and other intensive variables guiding dynamics. The idea that the direction of evolution can be read from the distribution of states, rather than from an external clock, aligns well with the theme of relaxation. Systems move toward more typical configurations under their own definitions of typicality. Reversibility at the microscopic scale raises a classic challenge. If one were to take the positions and velocities of all particles in a gas at a given instant and reverse their momenta exactly, the future would unwind the past. The escape from this paradox lies in practice. Perfect reversal requires coordination beyond reach, and any rounding error steers the system back toward typical behavior. Coarse graining, the act of ignoring irrelevant micro-detail, is built into measurement and into the very definition of macro states. The arrow is therefore a property of description as much as it is a property of dynamics. This does not diminish its reality, it clarifies its domain. The psychological sense of time follows the same gradient. Memory accumulates records about what has happened, not what will happen, because recording leaves traces that add to entropy. Prediction relies on models and probabilities, whereas recollection reads marks laid down in matter. Neural networks in a brain consume energy to maintain patterns and to rewrite them, with heat as the unavoidable companion. The feeling of flow, though still a subject for philosophy and biology, finds its anchor in the asymmetry of record-making. Minds move with the current set by the statistics of microstates. Across cosmic distances, the arrow sets a direction for history. Dense clouds collapse to form stars because gravity gathers matter more effectively than random motion can undo the gathering. Nuclear processes ignite, heavy elements forge, and later those elements mix into new clouds when stars shed envelopes or explode. Planets condense, atmospheres evolve, oceans exchange heat with skies, and organisms emerge to harvest gradients. The large structure of the universe relaxes toward ever more diffuse arrangements, even as local motors produce intricate patterns. Ultimately, stars fade, orbits widen through radiation of waves and particles, and matter drifts toward states where changes slow to glacial tempos. The path is a long, gentle slope rather than a cliff. In the midst of these vast motions, a single lesson soothes. The direction called future is not imposed by decree. It results from a preference that is both statistical and compassionate toward uncertainty. Systems do not reach for exact balances at all times. They allow variation and then accept the most probable outcome over many steps. The The same willingness to let probability speak reduces anxiety about the world's behavior. One can rely on cooling, mixing, and relaxing without fearing that they will spontaneously reverse in any relevant span. The arrow points with a steady hand, and the landscape it reveals is one where rest settles in as gradients diminish, where warmth spreads gently until differences fade, and where records bloom and fade in cycles that respect the cost of keeping them. Vacuum sounds like a nothing, an emptiness that leaves no trace. The deeper lesson is that emptiness possesses character. The stage on which galaxies drift carries an energy that does not dilute when matter thins and light stretches. This quiet energy acts with a sign that surprises. Instead of pulling masses together, it pushes the fabric outward with a steady hand. Pressure in most substances resists compression. Pressure in this vacuum energy is negative, which means it gravitates with a strange effect, accelerating the expansion rather than slowing it. The result is a universe that relaxes faster over time, as if space itself sighs and lengthens between distant clusters. The mathematics that describes this effect is economical. Add a term to the field equations that multiplies the metric by a constant. The constant sets a density that remains the same no matter how widely matter spreads. Because the source of curvature now includes this uniform energy, the solutions shift. A cosmos with sufficient vacuum energy expands in such a way that distances between faraway galaxies grow at an increasing rate. Observers detect that rate by comparing the brightness and redshift of standardizable candles, by mapping how structures assemble across time, and by following the angular pattern of the ancient afterglow. The collected evidence favors a component that behaves like a cosmological constant, a nearly time-independent contribution with an equation of state close to -1. Negative pressure sounds like a trick of words, yet its meaning is straightforward in the fluid picture of the universe. Energy density tells gravity how much there is to curve the stage, while pressure contributes as well, adding to the source when it is positive, subtracting when it is negative. Radiation with positive pressure slows expansion more than dust does. Vacuum energy with negative pressure reverses that tendency. The equations translate this bookkeeping into a slow acceleration that reveals itself only across billions of years. No local lab sees objects pushed apart by a measurable force from vacuum energy, because the effect is minuscule on small scales. The expansion becomes noticeable over intergalactic gulfs, where gravity between clusters weakens and the cumulative urging of the vacuum wins. A constant vacuum energy gives rise to a particular geometry with a gentle horizon. In such a realm, observers find that some regions recede so quickly that signals emitted now will never reach them. This horizon is not an object placed in space. It is a limit on communication set by accelerated growth of distances. The future in that case approaches a condition where the density of matter and radiation thins towards zero while the vacuum term remains, leaving a persistent, uniform hum in the equations. Galaxies not gravitationally bound to one another drift beyond contact. The night sky, already quiet, becomes emptier to any patient astronomer living in some far epoch. Local groups remain, stars age, and the wider web becomes a memory hidden beyond a reachable shell. The physical origin of this vacuum energy invites careful thought. Quantum field theory suggests that even in the lowest energy state, fields fluctuate. Virtual pairs appear and vanish, and the zero-point energies of modes sum to an enormous value if tallied without restraint. That naive sum would curve the universe beyond recognition, yet observations clearly require a very small value. The enormous mismatch points to missing pieces in the theoretical accounting, or to cancellations hidden in a deeper theory that unifies gravity with quantum fields. Some hints appear in controlled settings. Plates placed very close together alter the allowed modes of a field between them and experience a tiny attraction, a laboratory effect that shows vacuum fluctuations have consequences. Still, the leap from that confined geometry to the cosmic value of vacuum energy remains a leap with unknown steps. Another possibility allows the vacuum effect to vary slowly. A field that rolls down a shallow potential can act like a fluid with negative pressure. If the roll is gentle, the pressure approaches minus the energy density, and the effect closely mimics a cosmological constant. If the roll changes, the pressure and energy shift in time, leading to a history of acceleration that could be traced by precise measurements of distances and structure growth. This scenario, often called quintessence, adds a degree of freedom to the cosmic ledger. Its distinguishing marks would be a small drift in the equation of state, and perhaps subtle imprints on clustering, provided the field couples only weakly to matter. Instruments scan for these signs in the sky's statistics, using multiple methods to avoid confusion from any one approach. Geometry also gives room for more exotic pressures. Inhomogeneities and backreaction can, in principle, modify large-scale dynamics when averaged over. The challenge is to compute the effect reliably and to separate it from ordinary structure formation. So far, the simplest interpretation remains that a uniform component with negative pressure drives the observed acceleration, yet the door stays open for refinements if future data demand them. The attitude mirrors the subject. It prefers patience to spectacle. It waits for the cosmos to disclose its preference through repeated, consistent measurements. Practical consequences appear in the distribution of galaxies. As the vacuum term becomes more influential, the growth of structure slows. Gravity has less time and less effective force to assemble matter into deeper wells. Surveys map this balance by measuring how cluster counts change with redshift and how weak lensing shears trace the evolving web. The same tug of vacuum energy leaves signatures in the pattern of baryon acoustic oscillations because the scale set by early sound waves becomes a ruler whose apparent length depends on the expansion history. The agreement among these methods provides reassurance that the calm pressure they infer is not a mirage of one instrument or one assumption. Local environments do not surrender to the vacuum's push. The solar system, galaxies, and bound clusters remain intact. Their internal gravities hold them together against the slow outward urging that acts only across great spans. The picture is one of nested regimes. Within gravitational wells, dynamics play out according to nearby mass. Between wells, the metric expands, and the distances lengthen in measured increments set by the cosmic scale factor. This nested calm allows star formation to continue, planets to orbit, and observers to take measurements even as the global story arcs toward a more diffuse future. There is an old puzzle wrapped inside the new calm. Why is the vacuum energy so small in natural units, and why is it not exactly zero? A constant precisely at zero would save theorists the embarrassment of large cancellations. A large constant would have prevented galaxies from forming. The value implied by observations sits in a narrow window that allows early structure, then later acceleration. Some suggest that selection effects play a role, that observers arise in regions where values permit long-lived stars and heavy elements. Others search for mechanisms in high-energy theories that pin the vacuum term to a tiny number. The question persists like a soft tone beneath the music of measurements. The fate implied by a true cosmological constant is serene and sparse. Clusters fall away beyond horizons, and star formation wanes as gas is used up or locked in remnants. Stellar corpses cool for immense spans. Black holes slowly lose mass through quantum processes, so slow they make ages of galaxies feel brief. The sky from any remaining island would grow dark except for local fires, and even those would eventually dim. Temperature differences flatten, and processes move toward equilibrium with the vacuum's steady expansion as a fixed backdrop. In that distant era, time would still pass, but events would space themselves so widely that the notion of history would thin. If the vacuum energy is not exactly constant, alternate futures arise. A gently declining pressure could allow structure growth to resume in some measure. A rising dark energy could lead to an ever stronger acceleration that tears bound systems, though such scenarios are bounded by current data. Oscillating models, coupled fields, and modified gravity proposals have been written down, each with distinct predictions in detail. The adjudication comes from the sky. Distances, lensing, clustering, and the pattern of ancient light together test these possibilities with increasing subtlety. Through all the speculation, one image remains restful. The vacuum acts like a background breeze, too faint to ruffle leaves near a sheltered courtyard, yet steady across the open plain. It neither demands attention in daily motion nor relents when watched for eons. It writes a quiet term into the equations and steps back, letting the consequences unfold. Acceleration is not a sprint. It is the slow lengthening of intervals, the measured stretching of the grid on which galaxies are plotted. That stretching frames existence without intruding on the close work of stars and stones. A person can look up, understand that a deep, calm pressure is at work, and feel the mind settle into the same patient tempo, trusting that the stage will widen gently while familiar orbits keep their appointments. A mystery about uniformity invites a story about a brief, decisive swell. Imagine a field that pervades space, storing energy as a gentle plateau in its potential. If this field sits high on that plateau, the pressure it exerts is negative, and the equations of gravity respond by letting the scale factor grow almost exponentially. Distances between co-moving points double and double again in a tiny fraction of a second. This surge is not a burst of chaotic motion. It is a near-constant expansion rate that irons creases flat. Regions that once could exchange signals are stretched far beyond each other's horizons, yet they began as neighbors. Smoothness on the largest scales becomes natural, because what looks widely separated now was once in causal contact long enough to share temperature and settle into uniformity. The geometry follows suit. Curvature dilutes rapidly under this expansion. Any initial deviation from flatness shrinks towards zero as the inflating scale factor suppresses spatial curvature relative to the total energy density. A universe that might have begun with slight positive or negative curvature emerges from the swell looking almost flat. The delicate balance observed in the large-scale structure of space does not require a precisely tuned starting line. It results from the way rapid growth washes away initial geometric quirks while the field's energy dominates the budget. The mechanism rests on the field rolling slowly. If the slope of the potential is shallow and the friction from the expansion is large, the field descends in small steps while its potential energy stays nearly constant. The expansion rate then remains almost steady for many e-folds, a term that counts how many times distances multiply by the base of natural logarithms. A few dozen e-folds suffice to stretch an initial patch to a size that envelops the visible cosmos today. During this interval, inhomogeneities are diluted, defects are stretched away, and the horizon problem becomes a simple consequence of earlier proximity. Quantum fluctuations enter as quiet seeds. The field is not perfectly smooth at the smallest scales. Uncertainty grants it tiny excursions around the average value. During the swell, modes of these fluctuations are stretched beyond the horizon. They freeze with amplitudes set by the expansion rate, then later re-enter the horizon as the universe decelerates after the swell ends. What began as microscopic jitters becomes macroscopic imprints in the density of matter and radiation. These imprints guide the later formation of galaxies and clusters. Their statistics are nearly Gaussian, and their power spectrum is close to scale, invariant with a slight tilt. The tilt reflects the gentle change in the expansion rate as the field rolls. The end of the swell needs a graceful exit. As the field approaches a steeper part of its potential, or as friction diminishes, it begins to move more rapidly. The potential energy converts into kinetic energy, and then into particles and radiation in a reheating phase. The universe transitions from a cold, rapidly expanding state dominated by vacuum-like energy to a hot, dense plasma where familiar thermal processes resume. In this way, the surge does not leave a barren desert. It lays down a uniform stage and then stocks it with the ingredients for atoms, stars, and chemistry. Observational fingerprints of this story appear in several places. The temperature and polarization patterns of the ancient afterglow show a spectrum of fluctuations consistent with a nearly scale invariant origin and with acoustic peaks whose phases align as expected when initial perturbations were planted in the curvature rather than in the relative number of photons and baryons. The slight tilt toward less power at smaller scales fits the idea of a field whose potential is not exactly flat. The upper limits on certain types of distortions and on non-Gaussian features rule out classes of models with sharp corners or multiple strongly interacting fields. These constraints funnel attention toward potentials that are smooth, shallow, and single-valued over the relevant range. One hope is to hear a faint choral part in polarization. Waves in the fabric of spacetime produced during the swell would leave a distinctive curl pattern at large angular scales. These B-mode signatures would measure the energy scale of the surge directly, because the amplitude of those waves depends on how fast the expansion proceeded. Experiments on mountaintops, in balloons, and in space look for this pattern with increasing sensitivity while filtering foreground dust and synchrotron emission. A detection would be a message from times far earlier than any star, and a non-detection already discards models that predict too strong a tensor background. There are also isocurvature modes to consider. If more than one field was active, fluctuations in relative number densities could have arisen. Their absence in current data encourages simpler pictures in which a single field set the stage. Yet many possibilities survive in the detailed shapes of potentials. Plateaus, hilltops, small field excursions, large field excursions, and gently broken symmetries each lead to different predictions for tilt, tensor amplitude, and higher-order correlators. The dialogue between instruments and theory continues as measurements refine the allowed region in parameter space. The concept can be extended in ways that raise philosophical questions. In some models, the field's random quantum walk can occasionally push it uphill, even as it mostly rolls down. Regions where it lingers inflate longer, creating a patchwork in which the surge never ends globally. Pocket universes peel off in bubbles where the field finally exits and reheats. Each bubble expands and cools according to its local potential. In this picture, a vast mosaic of domains may exist, each with its own low-energy constants, while the overarching swell continues elsewhere. The observable sky would occupy just one bubble. Although such scenarios reach beyond immediate test, they illustrate how a simple mechanism can spawn a diverse landscape while still delivering a uniform sky where observers arise. Alternatives to the basic swell have been proposed. Some consider contracting phases that bounce into expansion, hoping to achieve smoothing without a flat potential. Others modify gravity at high energies, or introduce non-standard sound speeds for the fluctuations. These efforts are guided by the same puzzles and constrained by the same data. The mainstream view remains that a rapid, early growth driven by a slowly rolling field is the most economical way to account for the calm background and its detailed ripples. Economy is not dogma. It is the preference for the minimal assumptions that fit all the numbers at once. The physics behind the field invites questions about origins. What sets the potential? How does it connect to known particles and interactions? High-energy theories offer candidates, from moduli associated with extra dimensions to axion, like fields with protected flat potentials. Symmetries can shield flatness from quantum corrections, and mechanisms such as large decay constants or alignments can permit the required gentle slope over many field values. These attempts aim to embed the swell within a broader framework, rather than treating it as a lone stage prop. Success would bring the early surge into conversation with particle colliders, cosmic rays, and dark matter searches. Thermal relics from reheating present another opportunity. If reheating was violent, it could generate a background of high-frequency gravitational waves, topological defects at low abundance, or characteristic distortions in the spectrum of the ancient light if energy was injected late. These signatures would complement the low-frequency tensor modes that arise during the swell itself. Each trace would reveal a different part of the transition from vacuum energy domination to the fireball of ordinary radiation. Instruments designed to listen across a wide range of frequencies, along with precise maps of the microwave spectrum, pursue these possibilities. On human scales, the story encourages a mindful steadiness. A brief interval of rapid, smooth growth can set the conditions for long epochs of organized evolution. There is no need for a chaotic storm to explain the gentle sameness of the vast. A patient field drifting down a shallow incline can do the work. The lesson is one of quiet efficacy. Small slopes, extended over the right interval, can transform beginnings without leaving scars. Later processes inherit a uniform stage where differences grow in a controlled way, producing structure without undermining coherence. In the end, the surge offers a lullaby for cosmology. It tells of a time when space itself took a deep, even breath, swelling in tempo with a single gentle driver. That breath smoothed the young universe, set its curvature near neutrality, and placed tiny, nearly scale-free marks upon it. Those marks grew into galaxies and clusters, while the background kept its calm tone. The theory does not demand applause. It asks to be weighed against patterns that the sky reveals. For now, the weight holds. A quiet inflationary swell remains the simplest way to explain why the night looks so evenly lit at its faintest level, and why the grand geometry feels as if it was ironed before the first atoms formed. In a dark laboratory, a single particle meets a choice of paths. A slit to the left, a slit to the right. When both are open, ripples cross and paint a pattern of alternating brightness on a distant screen. The pattern speaks of superposition, of one traveler exploring two routes at once and then interfering with itself. Open the windows to the room, let dust and air scatter from the particle, or place a very gentle light to watch it pass, and the pattern fades. The marks blur into a simple sum of two shadows. The miracle is not that interference exists. The miracle is that in ordinary life it almost never appears. The reason has a name with the softness of a breeze: decoherence. Quantum theory gives a wave function to systems. Left alone, that wave function evolves linearly and keeps all the delicate phase relations that allow amplitudes to add and cancel. The world, however, does not leave systems alone. Every object touches a sea of photons, phonons, molecules, fields, and vibrations. Each touch entangles the system with its surroundings, correlating particular states of the system with particular states of the environment. When this happens, phase relations between different alternatives smear out in the combined state. For an observer who has access only to the system and not to all the environmental degrees of freedom, the interference terms vanish from practical reach. What remains is a mixture that acts like a classical probability distribution over distinct outcomes. A more precise story uses density matrices. A pure state of the whole world includes coherent off-diagonal terms that encode phase information. Trace out the environment to obtain the reduced state of the system, and those off-diagonal elements decay in the basis singled out by the interaction. The decay can be quantified by master equations, often in a form called Lindblad, where a set of jump or diffusion operators drains coherence at rates determined by coupling strengths and environmental spectra. The basis that resists disturbance, the one in which coherence is lost most quickly between distinct alternatives, becomes the preferred or pointer basis. Pointer states are the ones least perturbed by monitoring from the surroundings. They behave like robust classical configurations. The selection of pointer states depends on the structure of the coupling. For a particle coupled to scattered photons that resolve position, localized wave packets are stable. For a harmonic oscillator weakly damped by a bath, coherent states with minimal uncertainty emerge as the resilient set. For spins coupled to fluctuating magnetic fields, eigenstates of the interaction align with the environment and survive. This environment-induced superselection picks out the variables that appear classical. Position, orientation, and field amplitude often win because they are the quantities that the world incessantly measures by scattering and emission. Timescales of decoherence are astonishing. A dust grain suspended in air loses phase coherence between positions separated by a micrometer in far less than a microsecond. Even in high vacuum, stray photons from room temperature walls can entangle with the grain fast enough to smear interference on times far shorter than any human perception. A macroscopic object such as a moon bathing in sunlight interacts with an unimaginable number of photons every second. Any quantum superposition of distinct locations for such an object would decohere on timescales effectively instantaneous. The classical appearance of the macroscopic world is not a separate law. It is the limit of relentless entanglement. Experiments trace this transition with care. Interference has been demonstrated with electrons, neutrons, and atoms passing through gratings. Larger molecules have taken their turn, including fullerenes that carry dozens of carbon atoms. As the size grows, the interferometers demand colder beams, higher vacuum, and darker chambers to suppress scattering. Superconducting circuits support superpositions of clockwise and counterclockwise currents. By shielding them from noise and cooling them close to absolute zero, coherent oscillations can be sustained and measured. Cavity quantum electrodynamics places single atoms in resonators where they exchange quanta with a field, and the damping of off-diagonal terms can be watched as a function of photon leaks. Each platform draws the same portrait. Coherence is a resource that depletes when contact with the environment grows. The Measurement Act finds its practical explanation here. A measuring device is a large system with many internal degrees of freedom. When it couples to a quantum system, distinct outcomes imprint distinct macroscopic marks, such as pointer positions or current pulses. These marks entangle rapidly with the ambient world. The reduced state of the measured system plus apparatus becomes a mixture of alternatives that do not interfere. Decoherence does not select a single outcome by decree. It suppresses interference between branches so thoroughly that each branch evolves as if alone. Interpretations of quantum theory differ on whether one branch is realized or many coexist. What they share is the recognition that environmental entanglement hides phase information and produces classical records with overwhelming reliability. Thermodynamics enters through entropy. When a system entangles with its surroundings, information about its phase relations flows outward. The entropy of the reduced state rises even if the combined state remains pure. The arrow of time traced by decoherence aligns with the broader increase of entropy discussed in macroscopic processes. Records formed in the environment, such as scattered photons that encode an object's position, proliferate in multiple copies. The redundancy of records underlies the sense of objectivity. Many observers can read the same property without disturbing the system because they each interrogate a different subset of environmental carriers. This idea, often called quantum Darwinism, explains how facts about the world become public, not because they existed as classical facts from the start, but because the environment broadcasts them in countless copies. Coherence can be protected, which is why quantum technologies are possible. Isolation is the first strategy. Vacuum chambers, cryogenic temperatures, electromagnetic shielding, and vibration control reduce unwanted couplings. Dynamical decoupling applies carefully timed pulses to average out slow noise. Error-correcting codes encode logical states in entangled combinations of physical qubits, detecting and correcting small deviations without reading the protected information. None of these tricks abolish decoherence. They lengthen coherence times enough to perform useful tasks. Quantum sensors, computers, and communication devices live in that negotiated truce between isolation and control. Continuous observation shapes dynamics in subtle ways. Monitor a system so frequently that it cannot evolve freely, and transitions can be suppressed. This quantum Zeno effect shows that measurement is not just a readout, but a coupling that alters motion. Weak measurements, which gather partial information gradually, blur the line between watching and disturbing. They produce noisy records that track an evolving state while nudging it along. The interplay between monitoring, feedback, and decoherence forms the heart of quantum control theory. Through it, fragile superpositions can be steered and stabilized against a turbulent backdrop. Gravitational effects have been suggested as a source of additional decoherence. Some proposals argue that superpositions of different mass distributions may be unstable in a way not captured by standard environmental models. Experiments with levitated nanoparticles, interferometry of massive objects, and precise tests of macroscopic superpositions aim to probe such possibilities. Results to date are consistent with ordinary mechanisms of entanglement and scattering, but the quest continues because gravity remains the least integrated of the fundamental interactions within quantum theory. Even gentle constraints will teach where classicality truly begins. The mathematics of open systems provides a shared language for all these situations. Starting from a system plus environment Hamiltonian, one derives effective equations for the system alone by averaging over the bath. Markovian approximations lead to exponential decays of coherence when memory effects are negligible. Non-Markovian baths feed back information and produce revivals. Spectral densities of the environment, ohmic or super-ohmic, tune the rates and the temperature dependence. Every laboratory platform writes its own parameters into these general forms, and every platform confirms the same underlying lesson. Coherence is a delicate order parameter for phase relations, and the world is a great mixer. The calm that follows from decoherence is emotional as well as technical. It shows why a table holds a fixed position and does not shimmer between alternatives, why a planet's orbit can be drawn with a line instead of a cloud, why measuring devices deliver repeatable outcomes. It dispels the fear that quantum indeterminacy must make everything vague. Indeterminacy remains, but it is channeled. Superpositions survive where isolation and design protect them. Elsewhere, entanglement spreads phase information so widely that it becomes inaccessible, and classical behavior emerges as a practical certainty. Yet mystery is not banished. The suppression of interference clarifies how alternatives cease to mingle. It does not pronounce on why an observer perceives a single definite event. That remaining question belongs to interpretation, to models of branching worlds, hidden variables, or objective collapse. Regardless of the chosen stance, the operational truth stays the same. When a system couples to an environment rich with degrees of freedom, the interference terms in the reduced description fade. Those that align with stable pointer states persist. Observation becomes record-making, and record-making becomes the route by which the world appears stable, shareable, and quiet. It is fitting to think of decoherence as a hush that descends on quivering strings. Microscopic phases hum with possibility, then the air around them absorbs the music until only a few steady notes remain. The steady notes are the classical variables that daily life depends upon. The hushed notes are not destroyed. They are dispersed into the environment's countless channels. To recover them would require reversing the motion of every molecule in the room and every photon in the sky. Such feats belong to dreams. In waking practice, the hush holds, and the world rests in forms that invite trust. A region can be perfectly quiet and still change everything. A black hole begins with the simplest description nature allows. Mass, charge, and spin set the exterior geometry. No other details of the matter that collapsed remain visible. This austerity is known as the no-hair principle. Outside the horizon, the field equations yield a smooth solution that curves space and time with an elegant economy. The horizon itself is not a wall of matter. It is a boundary in the map of events where outward-pointing light rays pause and then turn inward. Crossing it requires no drama for a freely falling traveler. The specialness is global rather than local. Escape routes simply cease to exist. Near this boundary, trajectories concentrate. Light that just misses capture loops around multiple times before escaping, creating a photon ring that circles the shadow cast against glowing gas. The ring is a geometric signature rather than a luminous object. It marks the brink between return and surrender, a precise contour written by null geodesics. Around rotating holes, that contour becomes lopsided. Frame dragging carries space itself around, so that light moving with the spin finds a different path length than light moving against it. The result is an asymmetric shadow and a ring whose brightness varies with direction. A compass rose drawn by rotation. Accretion gives the boundary a way to announce itself. Gas falling inward heats through compression and friction, glowing across the spectrum. Magnetic fields thread the plasma and tap rotational energy to launch jets that spear into interstellar space. These jets are not thrown by a solid surface. They are guided by fields anchored in swirling matter and twisted by rotation close to the horizon. Timing of flares, brightness distributions, and spectra encode the innermost stable orbits and the location of the plunge. In this way, a structure that cannot be seen directly becomes measurable through the choreography it imposes on nearby matter. Disturb a black hole and it rings. After a merger or a sudden shift in the mass distribution just outside the horizon, the geometry returns to equilibrium by emitting waves with specific frequencies and damping times. These quasi-normal modes depend only on mass and spin. Measuring them is like striking a bell and inferring its size and composition from the sound. A clean detection of multiple modes would check the no-hair principle with exquisite precision. Early observations have already captured the dominant note. The dream is a full chord that proves the simplicity of the final state beyond doubt. Area carries a rule that deepens the quiet authority of horizons. In classical evolution, the total horizon area of isolated wholes never decreases, merge two, and the final area exceeds the sum of the parents. Feed a hole, and its area grows. This behavior suggests an analogy with entropy. When quantum fields are allowed near the horizon, the analogy becomes an identity. The entropy of a black hole is proportional to its horizon area measured in square Planck lengths. The proportionality constant gives a temperature, and at that temperature, the hole radiates weakly. The radiation is thermal to leading order, implying that a hole in empty space slowly loses mass, though the timescale is extremely long for astrophysical masses. Temperature and entropy at a horizon pull together threads from geometry, quantum theory, and thermodynamics. The laws of black hole mechanics map onto the familiar laws of thermodynamics by a change of dictionary. Surface gravity plays the role of temperature. Area plays the role of entropy. The combined picture says that even geometry keeps account of states, although the microscopic meaning of those states remains a subject for deeper theory. In certain frameworks, counting can be carried out explicitly for special classes of holes, giving the precise area law and suggesting a holographic accounting where information lives on lower dimensional surfaces. Information poses a quiet riddle. If radiation is exactly thermal and carries no subtle correlations, then details of what fell into a hole are lost when the hole evaporates. Quantum theory insists that evolution should be unitary, conserving information globally. Reconciling these statements has motivated proposals that range from complementarity at horizons to microscopic descriptions in dual theories where no loss occurs. The resolution may involve correlations hidden in the outgoing radiation or a revised picture of locality near horizons. Whatever form the answer takes, the entropy and temperature relations seem secure, anchoring the discussion in measurable thermodynamic behavior. Rotation adds further texture. A spinning hole drags inertial frames so strongly that there exists an ergo region outside the horizon where no stationary observer can remain at rest relative to distant stars. Within this region, waves can extract rotational energy through superradiance. Scatter the right mode, and the reflected wave leaves with more energy than it brought, borrowing from the spin. In the presence of a confining mirror, real or effective, this can lead to an instability that amplifies the wave repeatedly. The cosmos does not provide perfect mirrors, yet the principle reveals how rotation enriches the behavior of fields near strong gravity. Even without an instability, superradiance shapes scattering and may limit how fast black holes can spin when immersed in certain particle backgrounds. Charge appears rarely in astrophysics because plasma discharges large imbalances swiftly, yet the charged solutions teach structure. They show how horizons and inner horizons can coexist and how causal structures change as parameters vary. They also warn that naive extensions toward the center lead beyond the reach of classical trust. The inner regions of exact solutions include features that are likely replaced by new physics when quantum effects and realistic matter are included. What endures is the outer calm. Far from the center, the geometry is smooth and reliable, guiding orbits and light with the precision of a well-tuned instrument. Observation has moved from inference to imaging. Radio interferometers that stitch together antennas across continents achieve resolutions fine enough to discern horizon-scale structures in nearby massive holes. The measured brightness, depressions, and ring-like features match the predictions of light bending around compact objects. Time variability at the scale of hours or days records the dance of hotspots in the inner flow and the bend of their trails by the curved background. Polarization maps reveal magnetic field geometries that thread the plasma and hint at the engines of jets. The pictures are not portraits of surfaces, they are portraits of geometry traced by light. Microlensing in the vicinity of black holes provides another probe. Flares generated by orbiting features in an accretion disk can be magnified briefly when they pass behind regions where light paths bunch. The magnification pattern and its timing depend on the lensing map set by the background geometry. Careful monitoring turns these transient boosts into constraints on inclination, spin, and the disk's inner structure. Each flare becomes a sounding pulse that reveals the shape of the deepest potential well in the galaxy. In the distant universe, supermassive black holes at the cores of young galaxies fuel quasars that outshine their hosts. Their spectra carry signatures of broad emission lines formed in fast-moving gas bound to the central mass. Reverberation mapping watches line responses to continuum changes and infers sizes and masses from time delays. These signals tell that giant holes assembled early and grew by accretion and mergers. The mass of the central object correlates with properties of the surrounding galactic bulge, suggesting feedback that regulates growth. The quiet teacher thus coordinates structure on scales far larger than its horizon. Tidal forces near smaller holes can be severe. A star on an unlucky orbit can be shredded when the gradient in gravity across its diameter exceeds the star's self-binding. The debris forms a temporary disk and flares across the spectrum. The light curve decays as the fallback rate drops. These events are laboratories for strong gravity and for the physics of transience. The soft glow of their tails, months or years after peak, tells of circularization and slow accretion. Again, the horizon itself remains unseen, yet the program it writes for matter remains legible. Speculation looks toward tests that might reveal whispers from quantum structure at horizons, searches for tiny deviations in ring-down spectra, for echoes after the main waveform, or for frequency shifts that cannot be produced by classical geometry probe possibilities where the boundary is not perfectly absorbing. Current observations are consistent with the clean classical picture. That consistency is informative. It narrows the space of allowed departures and confirms the grip of the field equations in regimes where curvature is fierce but horizons are far larger than the Planck scale. Across all these scenes, the defining mood is restraint. Black holes do not thrash. They set boundary conditions that nearby matter and fields must respect. They keep time through orbital frequencies that approach a finite limit as the last stable orbit is reached. They ring at predictable pitches after mergers. They grow by swallowing and shrink by radiating at a temperature far too low to notice in the astrophysical present. Their lessons come not from frenzy but from the clarity of simple rules applied in strong settings. The calm is instructional. A single parameter added to mass, such as spin, changes everything nearby, yet it does so through geometry that remains smooth and solvable outside the horizon. It helps to picture the horizon as a shoreline in a perfectly still tide. Waves arrive from afar, curve, and then some slip over the lip, never to return. The shoreline moves only when something else happens, such as the arrival of a river or the merging of two bays. Otherwise, it is an edge that grants shape to everything around it. Telescopes and detectors have learned to read that shape. In the reading, fear gives way to understanding. The dark center is not an angry heart. It is a patient boundary that teaches by the quiet discipline it imposes on space, time, and light. Tranquility can be weighed, not by hand, but by devices that cultivate stillness until reality speaks in whispers. A clock is the first instrument of this listening. An optical lattice clock cages thousands of cold atoms in a standing wave of light and interrogates a single narrow transition with a laser whose frequency drifts less in a day than a heartbeat shifts in a lifetime. The atoms answer with a resonance so sharp that a second can be sliced into quadrillions of even parts. A frequency comb bridges that optical rhythm to radio counts, linking the deep calm of a trapped atom to the circuitry of everyday timekeeping. Chains of such clocks, synchronized by fibers and satellites, map tiny differences in gravitational potential across landscapes. The tick rate becomes a topographic survey of time itself. A hill is revealed not only by contour lines, but by the fraction of a second that an atom gives back when lifted. Silence is engineered as carefully as accuracy. Ultrastable cavities hold lasers steady by locking their wavelengths to the vibration modes of glass or crystalline rods, cooled and insulated until thermal murmurs almost cease. Vacuum chambers reduce collisions. Magnetic shields tame fields that would tug on levels and shift them. Vibrations from footsteps and distant traffic are damped by nested suspensions. The apparatus becomes a temple where even a minor draft can spoil a ceremony. Within that sanctuary, time's rate is read, with purity sufficient to test gravitational redshift over the height of a staircase. Distance is measured with light that counts itself. Interferometers compare path lengths by splitting and recombining beams, letting crests line up or oppose. Each fringe that slides past tells of a fraction of a wavelength gained or lost. Long baseline systems extend this principle across continents. Radio telescopes, separated by oceans, record a quasar's flicker and later align the recordings with atomic time. The resulting virtual dish spans the Earth. With it, the position of a station shifts by millimeters when tectonic plates move, and the planet's rotation wobbles are traced in real time. The stability of space-time becomes a coordinate grid maintained by the sky. Gravity's hush is mapped by satellites that fly in formation. Two craft chase each other in low orbit, measuring their separation with microwaves or lasers so precisely that a lump of mass in the Himalaya or a drawdown of groundwater in a basin tugs on the measured distance. Month by month, the field is charted in harmonics and anomalies. Ice sheets thin, rivers swell and subside, and the planet's invisible shape of potential is redrawn like a slow breathing. Drag-free control lets a test mass float inside each satellite, while the shell moves around it to cancel the slightest push from solar photons or residual air. Accelerometers whisper the remaining forces, so the gravity map remains a portrait of Earth rather than of the spacecraft. Rotation is sensed by light that hurries differently along loops that turn. A ring laser gyroscope sends two beams on opposite circuits of a closed path. If the instrument rotates, one beam completes the loop faster, and the beat between them reveals the rate. Arrays of such rings measure the planet's subtle rotational jitter, monitoring tides raised by the moon and sun in the mantle and core. Optical fibers wound into large coils perform the same trick at smaller scales, guiding aircraft and ships along courses where landmarks are distant. The Sagnac effect, once a laboratory curiosity, becomes a global yardstick of inertial frames. Atom interferometers carry the idea of superposition into the service of metrology. A cloud of chilled atoms is split into two paths by pulses of light that imprint momentum. One path rises a little higher and experiences a slightly different gravitational potential. After a pause, pulses recombine the paths, and the probability of finding atoms in one state or another records the phase difference accumulated between the two routes. From this phase, gravity's local value is read out with exquisite sensitivity. Tilt the device, move it upward, or let a mass pass nearby, and the atoms register the change without contact. Gradiometers using two clouds separated in height measure the difference directly, isolating local features from broader trends. Tracking fleets of spacecraft turns interplanetary space into an instrument. Radio signals exchanged between antennas on Earth and distant probes return, with frequencies shifted by motion and by the geometry of curved time near the Sun and planets. When the transmitter's frequency is referenced to atomic time, the smallest drifts can be measured and tied to ephemerides. Masses of asteroids, parameters of planetary orbits, and the bending of signals along near-solar paths reveal themselves in residuals. Occultations of stars by planet atmospheres and rings add timing marks that refine models of distant weather and particle distributions, all of it derived from careful counting of cycles. Reflections from mirrors left on the moon make a yardstick for the solar system. Short laser pulses leap from observatories, kiss retroreflectors on the lunar surface, and return to photodetectors a little over 2 seconds later. The round-trip time changes by milliseconds as the Earth turns and the Moon wobbles. By integrating many returns through clear nights, the distance is fixed to millimeter accuracy. Tides in Earth's mantle, the slow recession of the Moon due to tidal friction, and subtle tests of gravity's rules take form in those numbers. The quiet between outgoing pulse and incoming answer is the space where metrology breathes. Gyroscopes cooled and polished until their sphericity rivals ideal geometry watch the twist of nearby spacetime as the planet spins and orbits. Their axes drift by arcseconds over a year, an effect predicted by geometry and measured by comparing the direction of spin to a guide star traced with superconducting magnetometers. Fluid dynamics within the instruments, patch effects on surfaces, and the tiniest torques from thermal gradients must be tamed. What remains is the frame's slow turn, an imprint of mass and motion on the scaffold of inertial directions. Sensors that listen to temperature from the first light of the universe are built like snowbound observatories. Bolometers made from film so thin, they survive only at a fraction of a degree above absolute zero measure the power in microwaves arriving from all directions. Polarizers and rotating half-wave plates analyze the polarization pattern, seeking faint curls and streaks behind a fog of emission from dust and electrons in the Milky Way. The sky is scanned again and again. Data are cleaned, maps are stitched, and the spectrum of fluctuations is assembled with statistical care. The instruments are not looking for spectacle. They are looking for slight departures from a uniform field, and in those departures, they read geometry and history. Networks of clocks, interferometers, and telescopes are bound by time transfer. Optical fibers carry stabilized light over hundreds of kilometers, delivering a local standard from one lab to another with fractional uncertainties of parts in a quintillion. Satellite links move time across oceans, corrected for ionospheric delays and relativistic effects. Timescales are computed from weighted averages of many clocks, then broadcast as the common reference that synchronizes science, commerce, and navigation. The architecture is redundant and calm, designed to preserve order through storms, power outages, and maintenance. A single standard is never a single device. It is a choir tuned to a common pitch. Deep underground, seismometers rest on bedrock and listen to the Earth's interior, but they also serve an astrophysical patience. Great quakes are filtered out of delicate measurements. Microseisms from ocean waves are subtracted from the hum that instruments must endure. Magnetic quiet zones restrict radio noise so faint celestial signals can be recorded. Vibration-isolated platforms float optics on active feedback. Laboratories take on the character of monasteries, where the prayer is to silence everything but the phenomenon of interest. Calibration is a ritual that keeps instruments honest. Lasers are compared against molecular transitions that serve as anchors. Mirrors are measured with interferometric microscopes to ensure that their figure introduces no whisper of bias. Antennas are pointed at calibrator sources, and their gains are traced against known fluxes. Clocks are intercompared in campaigns that last months, revealing drifts and sudden steps that are then corrected with transparency. The humility of calibration is part of the serenity of measurement. It accepts that devices age and environments change, and it answers with repeated checks that return the whole ensemble to accord. Signals are coaxed from noise by statistics that respect the symmetry of ignorance. Matched filters search for patterns of known shape. Cross-correlations between independent instruments suppress local disturbances and elevate shared events. Blind analyses hide the final answer until all procedures are frozen, preventing subconscious tuning toward a desired outcome. When a result emerges, it carries the assurance that the method was as calm as the physics it sought to reveal. The credibility of small effects depends as much on discipline as on ingenuity. Across these methods and machines, a common ethic appears. Do not force nature to shout. Invite it to whisper into rooms quiet enough to hear. Let atoms tell time. Let light count distance. Let freefall define straightness. Let weak fields drift test masses. Let distant quasars knit continents. Each instrument translates serenity into digits. The translation is careful, deliberate, and repeatable. The reward is a map of space and time, drawn not with thick strokes, but with lines so fine that the geometry's smoothness becomes visible, and the calm that seemed intangible becomes a sum of numbers on a page. A universe can be rehearsed inside a machine when equations become choreography and numbers become dancers. The rehearsal begins with a lattice, a three-dimensional grid or a swarm of particles laid across a virtual volume. Into this scene go the rules that govern motion, gravity, light, and gas. The stage is quiet. The clock ticks forward by small increments. At each tick, forces are computed and paths are nudged. From the arithmetic, a landscape rises. Filaments gather, voids open, and halos of dark matter condense like dew along invisible threads. The calm that appears at great scales is not imposed. It emerges as a statistical truth when many bodies follow simple steps again and again. Two families of techniques share the floor. One treats matter as particles that move under mutual gravity with a softening length to prevent artificial clumping at unphysical scales. The integrators advance positions and velocities using schemes that conserve energy and angular momentum as precisely as the time step allows. Symplectic methods are favored because they respect the geometry of phase space and keep long-term drifts small. The other family treats gas on a mesh or with smoothed particles. On a mesh, the fluid equations are solved with Riemann solvers that capture shocks, while adaptive refinement sharpens the grid where structures form. In smoothed particle hydrodynamics, each element carries density and temperature, and interactions are computed by kernels that blur quantities over neighbors. Both approaches can add cooling, heating, and chemical networks so that gas collapses, forms stars in dense nodes, and returns energy through supernovae that stir turbulence. Gravity alone would build a web that looks like frost on glass. Baryons complicate the picture with pressure, radiation, and feedback. Modeling that feedback is an art that balances subgrid rules with observed scaling relations. Star-forming regions inject energy and momentum into their surroundings. Black hole accretion at galactic centers drives outflows that regulate growth. These processes operate below the resolution of a full cosmological run, so they are represented by recipes tuned to match galaxy masses, metallicities, and sizes. The craft lies in writing recipes that are flexible yet constrained, preventing them from becoming arbitrary knobs. When successful, the simulated population of galaxies lines up with counts and colors recorded by surveys, and the background of ionizing radiation evolves in step with quasar and star formation histories. At smaller scales, numerical relativity calculates the merger of compact objects by solving the full field equations on a grid. Gauge choices keep coordinates well behaved. Excision or puncture methods handle the interior of horizons without letting singularities poison the calculation. Waveforms are extracted at large radii where the curvature is weak enough to define a clean signal. Matching these waveforms to detector data converts templates into masses and spins. The same codes follow the dynamics of neutron stars with equations of state that include nuclear physics, magnetic fields, and neutrino transport. Outflows and ejector compositions are then fed to radiative transfer codes that predict light curves and spectra for transient surveys to compare against their catalogues. Radiation itself can be simulated as packets or fields. Monte Carlo methods launch photon bundles through gas and dust, scattering and absorbing according to local properties. Moment methods evolve energy density and flux with closures that approximate the angular distribution. These approaches allow a virtual galaxy to glow realistically, with starlight reddened by dust lanes, ionized bubbles around young clusters, and X-rays from compact sources. When combined with cosmological initial conditions, the same tools repaint the early fog during reionization, showing how islands of transparency grow and merge as the first luminous sources rise. Initial conditions are seeded from measured statistics. A random field is drawn with a power spectrum that matches the one inferred from ancient light. The phases are set by rolling a controlled set of random numbers, and the amplitude of each mode encodes the small departures from perfect uniformity that gravity will amplify. The box is then scaled to co-moving coordinates, and the expansion of space is included in the integrator so that motion relative to the Hubble flow is captured correctly. By repeating the draw with different random seeds, or by changing the box size and mass resolution, ensembles of universes are generated. From these ensembles, average behaviors and rare events are studied with equal care. Convergence checks guard against illusions. The same scenario is computed at multiple resolutions and with different time steps. If the result shifts when the grid is refined or the particle count is increased, the model is not yet faithful. Physical predictions must stabilize as numerical parameters are improved. Conserved quantities are tracked to verify that solvers do not introduce or remove energy and momentum in ways that matter for the questions being asked. Where possible, benchmarks with analytic solutions validate code modules before they are assembled into giants. The hardware that enables these rehearsals is a quiet orchestra of processors and accelerators. Graphics units push particles and matrix operations at immense rates while consuming less power than general-purpose cores. Memory bandwidth becomes as important as raw flops, because moving data is often the costliest step. Codes are rewritten to keep calculations near the data, to avoid communication where possible, and to overlap transfers with arithmetic. Checkpoints save states to storage so long runs can survive interruptions. Random number generators are tested for quality and parallel safety to keep the draws independent across millions of threads. Bayesian inference wraps these simulations in a statistical framework. Observations with uncertainties become likelihoods that compare data to model predictions. Priors reflect physical constraints and prior measurements. Samplers explore parameter spaces that can span everything from the normalization of the power spectrum to the efficiency of feedback in dwarf galaxies. Direct evaluation at every point would be too slow, so emulators are trained as surrogates, learning the mapping from parameters to outputs based on a set of carefully chosen training runs. These emulators return predictions quickly with quantified error bars, turning the heavy machinery into a nimble partner for fitting. Chaos is present, but manageable. At the level of individual orbits, small changes in initial conditions can lead to divergent trajectories. At the level of statistical fields, the averages and correlations remain stable. This separation is accepted and used. Simulations are asked for distributions, not for the fate of a single star in a single halo. Even so, numerical noise is kept in check by careful integration and by symmetries in initial configurations. Random seeds are recorded so that a result can be reproduced exactly, then varied slightly to measure sensitivity. The discipline turns an inherently sensitive flow into a reliable engine for inference. Uncertainties are catalogued with frankness. Resolution limits, subgrid prescriptions, calibration sample choices, and cosmological parameter priors all propagate into the final plots. Sensitivity studies vary one element at a time to evaluate its imprint. Cross-checks run the same physics in independent codes written by different teams to guard against shared biases. Synthetic skies generated from the simulations are fed through virtual instruments that mimic selection effects and noise. The processed outputs are then compared to the processed observations so that like is compared with like. Agreement at that level carries more weight than agreement in idealized space. The fruit of these efforts is an atlas. It contains dark matter halos with density profiles that break from power laws near their centers. It shows how satellite galaxies are stripped of gas and stars when they orbit within larger hosts. It maps the circumgalactic medium as a reservoir that buffers inflow and outflow, setting the pace of star formation. It traces the metals blown by winds into the intergalactic medium, where they cool filaments and seed future generations of stars. It recounts the assembly of galaxy clusters, whose hot atmospheres imprint signatures on background microwaves. The atlas also includes discrepancies that inspire refinement, such as cores in dwarf galaxy density profiles or the diversity of rotation curves at fixed mass. Each tension tightens recipes and prompts new measurements. Calm appears in places that might have seemed irretrievable from complexity. The large-scale correlation function approaches a simple form at long distances, with a small bump at the acoustic scale that remains as a fossil of ancient sound. The velocity field smooths on large scales into a nearly potential flow. The abundance of halos as a function of mass follows a universal curve when scaled by growth. The cosmic star formation rate rises, peaks, and declines in a gentle arch that emerges again and again from different runs. These regularities are not forced. They are discovered and then explained by the interplay of gravity, expansion, and cooling. Tools born in this practice return favors to other fields. The same hydrodynamics solvers model weather on exoplanets and accretion onto young stars. The same radiative transfer lights up dusty star-forming regions and predicts spectra for infrared surveys. The same inference engines learn from gravitational wave catalogs and from pulsar timing arrays. A culture of open code and shared data has grown, with repositories that host initial conditions, snapshots, and analysis scripts. This openness strengthens trust and accelerates progress. Independent groups can verify claims, extend models, and repurpose modules for new questions. The quiet satisfaction of simulating is not the pride of creating a world, it is the humility of approximating one closely enough that its patterns become legible. When a virtual filament weaves through a box and matches the statistics of mapped galaxies, when a modeled merger produces a light curve that aligns with a telescope's nightly points, when a computed waveform overlays a detector's signal with no free shifts, the feeling is of recognition rather than invention. The machine has been taught to listen to equations, and the equations have spoken in forms that reality echoes. In the end, serenity in simulation arises from restraint. Equations are advanced by small steps, not leaps. Resolution is added where needed, not everywhere. Subgrid models are kept as simple as possible, then tested and paired. Parameters are inferred with priors that reflect knowledge rather than desire. The result is a laboratory for the cosmos, where the loud is achieved by summing many quiet increments, and where the overall picture remains smooth, even as countless details are resolved. Watching such a laboratory work brings a calm of its own, the feeling that complexity can be explored patiently until its broad shapes become clear and its fine textures can be appreciated without the fear of being lost. Every map has margins where ink thins and paper shows through. The calm geometry that guides planets and light possesses such margins, places where known rules predict their own failure. Equations that behave with grace in most conditions deliver infinities at the centers of idealized collapses and at the beginning of expansion when run backward in time. An infinity in a calculation is not a location in space. It is a sign that the description has gone beyond its jurisdiction. The remedy is not to declare the world broken, but to admit that new language is required, where curvature grows too fierce for continuity to survive unscathed. A natural scale suggests itself. Combine constants from gravity, quantum theory, and relativity, and a set of units appears in which length, time, and mass take special values. The Planck length is unimaginably small, far beyond direct probe. The Planck time is shorter than any interval the fastest instruments can resolve. The Planck mass is microscopic by daily standards, yet astronomical by particle terms. These numbers are not decorations. They are fence posts, indicating where familiar extrapolations lose credibility. As curvature approaches the scale set by these values, neither pure geometry nor ordinary quantum fields can be trusted alone. One picture proposes that the stage is not continuous at the shortest distances. Perhaps it is woven from loops or grains, a combinatorial fabric where area and volume come in discrete quanta. In such a setting, curvature cannot blow up to infinity, because the building blocks impose a minimum size. The equations that evolve geometry would then replace singularities with bounces or bridges, converting what appears as an end into a passage. Programs that pursue this idea define operators for area and volume whose spectra are discrete, and they solve constraints that ensure consistency with large-scale smoothness. The result is a sketch where the familiar manifold emerges from a deeper spin network, like cloth emerging from interlocked threads. Another storyline keeps the stage continuous, but changes the cast of fundamental actors. Instead of point particles, the theory assigns strings or extended objects whose vibrations correspond to known particles. The extended size softens interactions at high energy, preventing the point-like collisions that breed divergences. Consistency requires extra spatial dimensions that are curled tightly or arranged with special symmetries. In certain arrangement, mathematics reveals a remarkable duality. A gravitational theory in a higher dimensional volume can be equivalent to a non-gravitational theory living on the boundary of that volume. This holographic relation suggests that a count of states in a region is governed by its area rather than its volume, an echo of the thermodynamic accounting at horizons. Causality itself may be the primitive element. The proposal of a causal set replaces the continuum by a partially ordered collection of events, where the order encodes who can influence whom. Space-time becomes the large-scale limit of a discrete structure that respects the light cone. Geometry would be reconstructed statistically from the order and the number of elements. In such a world, small scales do not host distances to be subdivided. They host relations. The smooth metric arises as an average over many links, while the Planck scale appears as the density of events. Other approaches pursue the renormalization of gravity as if it were a quantum field to be tamed by a fixed point. If the coupling runs with energy and crosses a point where behavior becomes scale invariant, the theory could be predictive despite the usual obstacles. The phrase for this possibility is asymptotic safety. Flow equations track how the effective action changes with a cutoff that slides from low to high energy. If a finite number of parameters control the flow near the fixed point, the high-energy theory is determined by low-energy measurements. Gravity would then be well-behaved all the way up, with singularities avoided because the running coupling weakens their teeth. Space-time uncertainty offers yet another softener. If measurements of position and time are limited by quantum back reaction, so that attempts to resolve scales below a certain threshold only stir the background, then the foam of microgeometry blurs sharp features. Distance attempts to refine itself result in energy densities that curve the stage and spoil the very measurement being undertaken. Precision digs its own pit and stops. The outcome is not a wall but a haze, a limit on knowability that protects the calm of the macroscopic world by refusing to grant sharpness to the microscopic stage. These sketches of deep structure come with testable edges. Discreteness of area could lead to tiny modifications in the radiation from compact objects or to characteristic signatures in the polarization of ancient light. Extended objects and extra dimensions might leave imprints in high-energy scattering or alter the behavior of gravity at short ranges in precise torsion balances. Holographic dualities inspire calculations of strongly coupled fluids that can be compared with experiments in nuclei colliders and cold atom systems, giving credibility to the mathematics that will later be brought to bear on gravity. Asymptotic safety makes predictions for how couplings run that can be checked against precision cosmology. Causal sets could introduce minute fluctuations in arrival times of distant signals when averaged over many paths. Each hint sits at the edge of current sensitivity, which is where it must sit if the Planck scale is truly the boundary of detail. The beginning of expansion concentrates many of these themes. If the early stage of the universe explored energies near the Planck scale, then subtle traces might linger in the statistical properties of the oldest light. Non-Gaussianities, small deviations from simple random phases, could indicate multiple fields or unusual interactions in the primordial era. A low amplitude of primordial gravitational waves would set an upper bound on energy scales, while a detection would open a window into the dynamics of the earliest moments. Spectral distortions in the microwave background, if found, could record energy release long after the first light decoupled, perhaps from decays of relics that were born in a high-energy epoch. Horizons suggest a more domestic laboratory for these edges. If semi-classical calculations give a temperature and an entropy to a compact object's boundary, then any deeper theory must reproduce those numbers and refine them. Corrections to the area law could scale as the logarithm of area in Planck units or include inverse powers, depending on the microstates counted. The spectrum of ring-down modes might carry tiny shifts if the near-horizon region is altered by quantum structure. Stimulated or suppressed emission relative to pure blackbody radiation could betray interactions beyond the simple field picture. Current data favor the classical predictions, but improvements in sensitivity keep the search alive, and the absence of anomalies narrows the range of acceptable proposals. The interchange between geometry and information gains prominence at the margin. If a boundary stores the data that describe a region, then entanglement among quantum fields may stitch space itself. Patches with strong entanglement behave as if they are adjacent, while reduced entanglement loosens the connection. In this view, connectivity is not assumed. It is built from correlations. The measure of entanglement between regions maps to geometrical quantities like areas of minimal surfaces, making the bridge between statistics and shape literal. The calm of large-scale geometry would then be the macroscopic expression of a vast web of balanced quantum relationships. Even the notion of time invites revision under pressure. In formulations where dynamics is encoded in constraints rather than in an external clock, evolution can be recast as a flow with respect to internal degrees of freedom. Time becomes relational, a parameter that labels correlations among subsystems. At high energies, a variable that acts like time for one sector may falter for another. Choosing a clock becomes a choice of perspective rather than a unique fact. The usual arrow remains once coarse graining and entropy enter, but the foundation shows more flexibility than daily intuition suggests. What will ultimately replace infinities with finite features is unknown, yet the search has a consistent character. It aims to preserve the verified calm of large scales while removing the pathological pretense of endless curvature. It prefers principles that already hinted their power in less extreme contexts, such as unitarity, causality, and symmetry. It allows bold mathematical structures but demands that they reduce to the familiar where tests are possible. Above all, it treats the Planck regime not as a playground for speculation but as a limit where humility must rule. Because the distance between conjecture and observation is long, a traveller standing at a cliff's edge hears the ocean's steady breath below and feels the pull of open air. The edge of calm in spacetime is like that. The waves are quantum, the pull is gravity, and the horizon is an invitation to look down without falling. The language to describe the view is still being refined. Perhaps the sea will resolve into a mesh of relations. Perhaps it will reveal a continuous depth that only appears grainy to coarse senses. Perhaps dual descriptions will prove that different vantage points tell the same story with different words. Whatever the final grammar, the promise is that the map beyond the margin will keep the serenity that made the interior understandable. The smallest scales will possess their own order, and that order will smooth back into the gentle geometry that allows galaxies to drift and light, to travel straight until something massive persuades it to curve. Night gathers across rooftops and rivers, and bodies surrender their weight to mattresses and quiet chairs. Breath slows. The world outside a window becomes a soft lattice of lights and silhouettes. Within that stillness, the idea of sleeping in spacetime finds its natural home. Sleep is not a withdrawal from motion, it is a truce with it. The planet spins beneath bedrooms, tracing a circle that never asks to be noticed. The planet orbits a star that burns in steady thermonuclear patience. The star glides around a galactic center, and that larger journey continues through a web whose strands lengthen with the universe's expansion. A sleeper lies inside an architecture of motion that requires no effort, an architecture that keeps its promises whether eyes are open or closed. Time in a resting room is layered. The tempo inside a heart follows electrical pathways that fire and reset with regularity. The tempo outside is set by light's unchanging speed and gravity's soft calibration of seconds at different heights. Between them, circadian clocks keep a cycle tuned by dawn and dusk. These clocks are biochemical machines, sensitive to photons that slip through eyelids at morning and to darkness that removes their counsel at night. Their signal is the permission to rest. In that permission, metabolism slows, memory reorganizes, and muscles repair microscopic tears. The body participates in a principle that pervades the cosmos. Systems seek equilibrium, then drift from it, then return. Rest is the return. It helps to picture the bedroom as an observatory, only one that looks inward as much as outward. Dreams play across a cortex that quiets some circuits and allows others to associate with less constraint. In that play, the brain samples possibilities and consolidates patterns. The stories that unfold in sleep are not bound precisely by straight lines or synchronized clocks. They are sensitive to emotional gravity rather than to mass. Even so, their possibility rests on rules that protect continuity. Ion channels obey the same physics in the night as in the day. Molecules diffuse with the same Brownian patience. The chemical gradients that drive synapses mirror the gradients that drive winds and ocean currents, small differences that do work and then dissolve as their energy is spent. Peace in sleep borrows from a larger serenity. The room is quiet because air exerts friction that muffles distant disturbance. The walls stand because solids arrange their electrons into bonds that resist small displacements. The ceiling holds because gravity pulls down in a predictable way and because materials possess strength measured in numbers that do not drift overnight. This reliability rests on simple symmetries: conservation of energy, conservation of momentum, invariance of physical laws from one place to another. Each plays a role in letting a sleeper trust that morning will arrive where evening departed. The comfort is not sentimental. It is structural. Consider a traveler who crosses time zones. The body's clock lags, then slowly re-enters step with the light. The rate of resynchronization is not arbitrary. It depends on protein cycles shaped by natural selection and ultimately by chemistry's regularities. Consider a parent rocking a child. The rhythm that soothes is close to the tempo of a resting heart and the pace of unhurried walking, human scales that match the natural frequencies of bones and muscles. Consider the pulse of rain on a roof, or the slow swing of a pendulum clock. Each of these small rhythms organizes perception into intervals that feel safe. They are echoes of a larger organizing that the universe performs by keeping C constant and by letting curvature change time steadily rather than abruptly. There is a philosophical mercy in this. The cosmos offers reasons for trust that do not depend on authority. A person need not plead for a sunrise, the earth will rotate. A person need not instruct respiration, the medulla will pace the diaphragm. A person need not hold planets in their orbits by hope. Geometry takes care of that. Such assurances do not trivialize human worry or diminish grief. They provide a frame in which grief can be carried and worry can be set down without fear that reality will tear while attention wanders. The frame is a gentle scaffold, and sleep is the act of leaning into it. Mortality lends the frame its deepest meaning. Every life is finite. The atoms that make a hand and a voice were forged in stars, and those atoms will be used again long after names are remembered only by a few. Knowing this, the mind often asks for significance. The request can be answered quietly. Significance is not only in being large or permanent, it appears when small structures solve small problems with grace. A bee finding a flower in dawn light, a pianist practicing scales in a dim studio, a nurse adjusting a blanket in a ward, each is a local reduction of uncertainty, a local harvest of order from gradient. Each follows laws that apply equally to quasar winds and to the lensing of distant galaxies. The unity is the answer. The gentleness of space and time teaches a practice. Live in accordance with least unnecessary action. Align paths with available curves. Accept that some horizons are limits, not failures. Use clocks that are steady and compare them without resentment. Prefer transparency to noise. Measure when confused and rest when measurement is complete. This practice is not abstract. It looks like a scientist double-checking a calibration even when the plot already looks good. It looks like a teacher returning to a patient explanation rather than raising a voice. It looks like a builder leveling a foundation carefully because walls depend on it. A different calm arrives from the scale of the night sky. When a person stands in a field and looks up, the neural machinery that usually tracks threats and opportunities has little to grab. Points of light sit too far away for action or possession. The result is a cognitive easing, a reduction in urgency that opens the way to reflection. The eye adapts, colors drain, and rods take primacy. Stars appear where none seemed visible a minute before. That change is a lesson about perception. The world's quietness is sometimes there, awaiting patience rather than absent. Many problems admit such patience. With it, patterns become legible. There is also peace in accepting that some answers will not be delivered in one lifetime. The earliest moments of the universe, the unification of gravity with quantum rules, the precise nature of the energy that accelerates expansion, these are questions that a person can love without insisting on their immediate dissolution. The measure of a mind need not be the number of volts it forces open. It can be the quality of attention it brings to locks that are still being studied. A library can soothe because it holds books that will take years to read. The cosmos can soothe for the same reason. In the middle of the night, a clock on a shelf ticks in its slow way. Its second hand moves in jumps or in a smooth sweep, depending on its mechanism, but either way it reminds that time passes by accumulation, not by rush. Deep forces act in the same spirit. Mountains erode grain by grain. Continents drift centimeters a year. Orbits precess in tiny arcs through centuries. Even hearts change gradually, beat by beat, adapting to seasons and stresses in increments that allow equilibrium to be found again and again. The lesson is not to avoid haste when haste is needed. It is to honor the scale of processes by matching them with the right pace. A final picture completes the thought. Imagine a sleeper as a small boat moored in a gentle harbor. The tide rises and falls by fractions of a meter. The larger ocean beyond sends swells that enter as long waves, and the boat lifts and settles without strain. Far offshore, storms rage. But by the time their energy reaches the cove, it is softened by distance and contour. The mooring line holds because it was tied well, and the knot does not slip because friction and fiber were chosen wisely. The boat's hull gently creaks, and then the sound fades as wood and water come to agreement. In the morning, the same boat is ready to cross the bay. Sleeping in space-time is like that. The harbor is geometry, the tide is expansion. The swells are waves of many kinds, from weather to gravity, each diminished by long travel and by the buffering of structures close at hand. The line is trust in rules that continue to hold. The knot is the set of daily habits that keep bodies and rooms in repair. Rest becomes a participation in a larger order that does not depend on intention. When eyes close, the patient architecture continues its work. When eyes open, there is a new interval to live within, and the boat is ready to leave the harbor or to stay, as wisdom suggests. Let the room dim until edges soften and sounds fold into the hush that walls know. Let breath be counted, not as duty, but as tide, a gentle entering and leaving that needs no command. Outside, a planet turns in the dark, and that turning is enough to carry horizons across windows. Beyond the planet, a star maintains its quiet furnace, lifting light that will never tire of crossing the cold. Beyond the star, a city of stars rides on a spiral road, and the road follows a curve that harms no one. Let attention fall like a feather into the space behind the eyes. Thoughts will wander, then slow, then take the shape of simple pictures. A path through a grove, a shoreline that remembers footsteps, a sky that does not hurry its constellations. In those pictures, rules hold without noise. Straight lines remain straight unless patience asks them to bend. Clocks keep their hum and forgive small delays. Distances widen with a softness that asks for no apology. If worry arrives, greet it as weather, real and passing. The physics of clouds is not the sky. The sky is the frame that allows weather to transform without tearing. A mind can borrow that frame. It can hold its currents and gusts beneath a ceiling of quiet certainty. Gravity will not forget how to guide. Light will not forget how to travel. The heart will not forget how to rest. When weight begins to lift from limbs, remember this simple kindness. Existence happens inside a fabric that prefers coherence, that favors balance, that offers equilibrium again and again to those who seek it with steady hands. Close the book, set the glass beside the lamp, let the faithful grammar of space and time cradle the next few hours. The universe is not loud tonight. It keeps watch in silence. End of script. Sweet dreams.